On. Hi, good morning and welcome, Dr. Reddy.
Good morning, sir. Good morning.
How are you?
I am fine, fine, fine. Thank you.
How is the weather this evening in Canada?
Yeah, it's almost 9 now. Another next 2 months, like -5, -6. It depends.
Oh,
Yeah, not bad. So only outside is everywhere is ice. Yeah.
okay.
Just give me 1 minute. I'm coming 1 minute.
It's 9:30 now. Shall we
Yeah,
proceed
yeah,
to
yeah.
start the session?
Yeah,
Dr.
yeah.
Reddy?
1 minute. Yes, yes.
Hello? Dr. Reddy, can I proceed to start the session?
Yeah, yeah, yeah. Definitely, sir. Definitely.
Okay,
Yeah.
okay. Hello everyone, welcome you all again to the second day of 1 week long faculty development program on information and communication technologies for smart city applications. ICT is for Smart 2021, organized by Department of Electronics and Communication Engineering, NIT Silchar, and is sponsored by AICT New Delhi under ATAL FDP scheme. I extend my warm welcome to the first invited speaker of day 2 session, Dr. M.V. Reddy from Institute of Research Hydrocubic, Canada. Dr. Reddy obtained his PhD in 2003 with highest honors in the area of material science from University of Bordeaux, France. Dr. Reddy currently working as a senior researcher at Institute of Research Hydrocubic Center of Excellence in Transportation, Electrification and Energy Storage, Hydrocubic, Canada. Previously, during July 2003 to May 2019, he worked at National University of Singapore. Dr. Reddy had been working for the last 20 years on smart battery materials for different applications, electric vehicle, solar cell, sensor, catalysis and electrocatalysis, etc. And his research has been cited by 14,800 researchers throughout the globe and has 63H index. He has published around 200 papers in various international journals. He has delivered around 100 talks at various conferences and conducted few workshops, including Gyan courses on on battery materials. He is serving as editorial advisory board member in Material Research Bulletin and Journal of Energy Storage and several other open access journals. He served as a theme chair for energy and environment during 2012 and session chair for batteries, supercapacitors, and fuel cells during 2012, 14, and 16, and materials for environmental protection during 2012 in International Conference of Young Researchers on Advanced Materials. His project won many awards, including 10 gold, 8 silver, 6 bronze, and many prizes in national and international conferences. Dr. Reddy won Outstanding Science Mentorship Award 2018 to 2008, 2010 to 2018 from Ministry of Education Singapore and Inspiring Research Mentor Award 2011 to 2019 from National University of Singapore. Recently, Dr. Reddy is mentioned among top 2% highly cited researchers in the area of energy in the year 2020. With this, I welcome and invite Dr. Reddy to start the session.
Okay. Okay. Thank you very much, and good morning, everybody. Thank you. So I would like to share my slides, sir.
Yes, sir. Yes, sir, please.
Okay. Now I'm allowed. Yeah. Presentation now.
Okay. Then entire screen.
Yes.
Click on that one. Okay.
Okay. Hello. Yes, my slide is visible now, sir.
Yes, now it is coming.
Is okay?
Yes, sir. Yes, it is okay. On your on top of your slide, one icon is there. You please hide that icon. Not stop. Hide.
Yeah.
Hide. Right side
Yeah.
one icon. Yes, yes, yes. Please.
Okay.
Okay. Thank you. Go ahead, please.
So again, good morning, everybody, and thank you, Professor, for his kind invitation. In fact, it's the first time I'm giving talk in Assam. In fact, so COVID makes us to give some whatever the research I've been working for the last 20 years. Although this conference is an information science, and then here in the area of the smart battery, I'm going to at least some few examples are useful for you, especially for young researcher. Since I trained in the area of material science and some, especially microbatteries, those batteries are used for the MEMS applications. And also some techniques are maybe useful for your future research. In fact, suppose you want to design any sensor or any other type of what they call as the thin films, you may need some characterization technique that will be very useful. In overall, in summary, I can tell that some, especially for hybrid vehicles or autonomous electric vehicles, so there is a combination of both the materials engineers and electronic and communication engineer. So at the end, as I suggested yesterday, the director, your director, I think nowadays is a multidisciplinary. I'm going to touch some examples about what is the multidisciplinary research, what you can do. You can concentrate both the materials and electronic engineers. So this is our outline of my talk. So I think this is where we're coming from Canada, almost next to the American border. So Quebec is a very French and French-speaking colony, and especially here, sometimes it will go to temperature. It may goes to like few days, 10 to 15 days per year. It will go to like almost like minus 25 degrees, and sometimes other four type of climates we can see throughout the year. So regarding Hydro-Quebec, in fact, we work with mainly green electrical, renewable energy like hydroelectricity. So our institute is working on mainly what they call as materials for electric vehicles, and especially power electronics. Some people are working with and charging station, etc. Here, I think at the end, I think all people are working on the renewable energy. In fact, in a different way, we are contributing to the community. In addition to this one, this Hydro-Quebec has been closely collaboration with well-known university in McGill and other university within Montreal, and then few are in Canada. So in fact, I'm going to, in fact, although previously I mentioned that I was involved in the material research organization, in fact, we help them including the conference organization. In fact, I can tell that Professor Tamur suggested that I think workshop or conference organization is very important for, especially for any researchers, especially for learning point of view. It is good. I think that is nice for this type of presentation will be very useful for us to learn new things for the future research, or like if we go for industry, etc. So I would like to thank you some of the people, top here, a few people from the those PhD students, and bottom there are the students from the high school. In fact, you can see that. So at the end, Singapore is a people are telling a smart country. It's a very small country. Within 40 kilometers, anybody can access. Advantage of this one is that anyway, so that so they don't waste much time with especially travel, etc. So at the end, these students yearly they're able to spend the research in the especially engineering or any projects they want. So at the end, so in terms, I think we were able to get some small funding that is enough to run the lab. So that way, in addition to these students, they're able to present in the national and international conferences here. Idea here is that we have to train them for the area, but at least they can go for science and engineering projects. Like future, they can select mainly some people are now electrical engineers and mechanical engineers. So idea here is that at the end, younger level, just we motivate them to do research in the area of their interest. And also we have been some collaboration within the India as different parts of the world. Also you can see I work with the faculty of engineering and then especially physicist and chemist, etc. So now I'm going to introduce the topic. I think now based on the UN National Report, World Urbanization Prospect Report. So I think it's in 2018. So 55% of the population lives in urban areas, and it is expected to reach nearly by 68%. Anyway, it will vary depending on the area to area. So these are all by UN report. So cities face a major challenges in maintaining sustainable environment, especially healthy lifestyle, and required for infrastructure, especially creating the resources and demand, including the waste management and required services, especially for example, all type of what they call a smart things. And also smart city concept has been changing from time to time. People are initially they started intelligent, then digital, smart, now sustainable smart and smart sustainable, etc. So in conclusion, it is like a trend is nothing but smart city is a trend in the integrating the ideas of smart mobility, smart economy, and smart people, and smart government, and smart environment, and smart living at the end. So again, so the development of new technologies are needed for the smart vehicles in the area of smart building, especially 5G technology. Now the people are going for 6G and sensors. I think yesterday, I think we the very interesting talks has been by the previous speakers, and especially Internet of Things, and especially GIS and global positioning systems and artificial intelligence, robotic, and these are all the at the end we call as smart electricity. In fact, we need especially it should be renewable and especially for vehicular technology. Again, smart city must adopt the renewable technology, specifically before solar or hydro, or if you want the batteries technology, etc. So again, so these are the technologies are needed to especially want to heat or cool or transportation applications. At the end, these materials should be what they call not dangerous. It means that no greenhouse gas emissions. So and also no pollution. So it should be everything should be green. So these are all the technology we call as a smart city. In fact, it is difficult to see all the criteria. Still, it is a way of all our people nowadays throughout the world. I think people are doing that this type of smart infrastructure for the in different ways. So one example, since the topic is on electric vehicles, so on the smart cities, nothing but so you can see here. So bottom corner, so the smart like building. If there is a sensors, here it come electrical people, and also here, and for example, wind energy. Here, the smart building in the sense that it is smart building. People are thinking that it's the big batteries. You should be store the battery from the solar energy or wind energy, so that the grid smart grids, and we can use it for the residential applications as well as industry. Anyway, that is a little bit difficult because sometimes you need a lot of energy. So overall, smart in the meanings everything should be what they call as smart, sustainable, including that internet and what they call as all the type of technology, etc. So again, so I will give some in rough idea about how much energy needed. For example, smart grid application we need a nearly megawatt hour range. especially plug-in hybrid vehicles, nearly 10 to 100 kilowatt hour. Portable electronic sources, we need nearly 1 to 100 watt hour. And especially medical devices, we need 1 to 500 milliwatt hour. Again, this smart, what they call as the electric vehicles, it will be, we can reduce the pollutions, with especially within these cities. For example, presently, I think we all over the world, especially major cities, are facing the problem about the pollutions due to the gasoline. That's why people are looking to the alternative uh, vehicles, especially for electric vehicles. There are the alternative vehicles. Here, there is a summary. There is a total energy consumption and CO2 emission with a different type of the sources, starting from the car, taxi, buses, etc. Another smart city, it contains there is a solar cells. Here I want to tell you that solar cells. So there is a three different varieties. Among them, here I wanted to I discussed some people, a few talks. Many solar people are telling that. So main technology they have a nice problem is there is more expensive due to the battery pack, in the sense that most of the cost is going for a battery pack. So that's why, so they we want to, I think people are nearly 2 to 3 times reduction of the what the cost is needed for the uh, smart applications. And another thing is that if your water is there, if you're using photocatalytic water splitting technology, in fact, there are a lot of challenges are there, and sometimes yield, so many things are there. And see, this is in terms of the material prospects. And again, another example is any smart city development should be material should be recyclable. I think another, if you use a green concept, it will be very useful for the uh, long time technology. So another very important one, I think, since electrical engineers already know that the vertical autonomous vehicle is a self-driving vehicles, uses artificial intelligence software and light detection, ranging, and radar sensing technology. In fact, compared to by using these driverless cars, the people are thinking the lowering the fuel consumption, as well as a development for the future smart cities, and also reduce the CO2 emission, because since it uses a car battery, and especially we can reduce the traffic congestion. So, so these are predicted what they call as annual revenue, as well as growth in the autonomous vehicles. I think people are predicting that we can we can reduce the especially crashes by using this, since the sensors are very accurate, it will detect properly. That is why. So there is extensive research is going on the all over the world, especially major companies. Now, presently the cost is a major issue, highest cost, and some of the things, especially growth, connectivity, especially infrastructure is very important. Suppose, for example, 5G technology with the proper internet facility, with all the things are needed for the. So these are the good smart city infrastructure is also play an important role. So, and for example, and for especially, so this is one example. Since the autonomous vehicles, it contains here, I think, main role with electrical communication engineers will play an important role in developing the especially cameras or GPS system. At the end, there is a computer. So all this one, it will play an important role. In fact, you want to integrate the things, not only battery. I think we need electrical engineers. So that's why it is a multidisciplinary research area. We can focus in a different aspects. So again, I think these are the different terms. I think all people knows, since you people are working with electronic engineering, so this is not needed. And I think these are various companies are investing. You can see that there is a huge investment with all over the world, because since the people are thinking that they can get huge like profit in a future way. That's why all over the world people are spending in especially patent technology, etc. So now, so it's very important thing is, and summary is that I'm going to increase the materials. In fact, our human history started in the Stone Age, Copper Age, bronze, and iron, and silicon. In fact, silicon is a real thing. So it's been changed a lot, especially for the vacuum tubes and computer, and then IC circuits, and then discovery of the mobile phones or battery material, etc. At the end, now recently, energy, sensor, what they call environment and healthcare. These are the very important areas are concentrated. So in conclusion, at the end, I'm going to tell based on the utility, the materials are broadly classified based on utility as well as physical properties. Utilities, for example, sand, wood, in fact, it is very important. We need a sand, concrete, granite, etc. And electronic material, for example, silicon, germanium, and energetic materials and engineering materials. In fact, these are all like especially lightweight materials are needed for especially smart building, etc., etc. Since is more on the what they call engineering one. So materials, especially metal, semiconductor, insulators, and magnetic material, especially optical material. For example, you want to sensing, we need optical material and dielectric material, radioactive, and then energy material. Especially, you want to store the things, we need a good energy material. So this is a slide. It will tell that research is needed for the materials for the smart cities. For example, smart material for thermal insulation, especially heating and cooling of the building is needed, and materials for printing, especially now people wants to be 3D printing, and especially people want to be energy saving of the light. So again, the electrical engineer will play an important role. And smart glass is very important. So because we want to be, so glass should be we can store the, especially want to the solar cell research, as well as change the color depending on the like on and off. I'm going to tell some example about the electrochromic applications. And flexible organic means that any material or anything, you should, for example, in solar cells should be wearable. So they want to be, or any battery should be flexible and it is wearable. They call as a, and especially solar cells. Again, it is very important for material for resistive switching memories. In fact, for example, the titanium. So there are all the things that we use, and sensor materials for the lidar technology, and especially graphene nowadays. I think yesterday people have been talked about the graphene and CNT, but again, some limitations are there in all the, because sometimes mechanical properties, so many things you take into consideration. In fact, as an academic researcher, it is our duty to train the young students, make sure that give a proper fundamental ideas, and depending on the application available facilities, they can do the research or the master projects or MTech or BTech projects, or further they're doing the research. So at the end, materials for electric vehicles or EV chargers, these are very important. In fact, there is a extensive research is going on all over the world. So the one slide is very important. In fact, if you design any smart materials for any or smart cities, for including electrical vehicles or electric grid, so these are very important in a smart batteries needed. So mainly looking for the, we need a high capacity. It should be lightweight. Is a very important criteria. And at the end, we need high energy density and power density. I'm going to touch up what is the meaning of energy density. And long life, it is very important. Nowadays, I think people are predicting to 15 to 20 years. I think it is nice, it will go more than 50 to 40 to 50. I'll tell you what is the real problem with these materials. And again is the fast charging. So nowadays, I think I know that mobile phones, if you take, I think we have to wait for maybe nowadays, compared to olden times, now we have to wait for more time, especially fast charging. Also, there is a possibility you charge a battery within 5 minutes or 2 minutes, so or 1 second is a question mark. The reason is, I'll tell you, because these are the solids. Fast charging is a little bit difficult. Nowadays, I think there is extensive research going on how to improve the fast charging. So especially the material electronic conductor development is going on. And impedance is the main thing. In fact, what they call a resistance of the cell should be low as possible. I'll tell you some few example what is the meaning of resistance. And Coulombic efficiency is like around 98%, you'll get it. 100% is difficult. Again, at the end is very important. Any battery, any smart battery or your sensor devices, it is to adapt the climate geographical condition, in the sense that sometimes, especially India, temperature it may go to 45 to 50 degree. So the problem is the electrolyte is there. So if you go to high temperature, there is a problem with the explosion, or sometimes the leakage of the electrolyte. Or if you go to lower voltage, the electrolyte will freeze off, so automatically conductivity will be low, and sometimes battery may not run, or it will make an insulating layer. So there is a little bit problems with respect to this type of material. That's why there is a, depending on the climate conditions, there is additional circuit, especially increase what they call a temperature, like especially to heating or cooling system is needed for the each battery. At the end, after solving all this one, we need a more safer material, low cost, and toxic. So this is a very important criteria for to to use any smart meter. Meaning of smart means at the end it is very important. If you do any smart battery, it should be recyclable. It's not like we can throw out in the dustbin again. You're making pollution. So that's why these are all the materials should be smart, and we can do what we call a circular economy will play an important role. So one slide it may tell that why lithium batteries, why don't you use lead acid battery? You may ask lead is very cheaper. And the main here is that, for example, the space applications or your mobile phones, your battery should be lightweight, and it should be, the reason is that the lithium is very lightweight and higher energy dense because they call as volumetric and then gravimetric dense. So that's why because of this speciality, I think that's why it is more popular with different type of applications. So this is the voltage of the cell with respect. That's why we nearly 3.7 or 4 volts will get based on the lithium based cell. I'll tell you how to calculate the energy density with the next few slides. So that will be very useful for you. Okay. So again, so materials are same. So the thing is that if you use your mobile phones or your laptop, material is same. Only what they call casing or design will be different. So if you go for hybrid vehicles, again, 18650 cells are clubbed together depending on how much energy requirement they will do. So that is the way they will do. So these are the different configuration available. In fact, if you go for grid, again, it is a little bit bigger way. So again, the material is same. So for example, if you're using nearly 3.7 volts, it belongs to your mobile phones. I think you may see. I'll tell you inside what is there in a positive and negative in the later slide. And sometimes if you use your what they call as a laptop, there is a cylindrical 18650 cell is there inside. And again, if you depending on the energy, I think people can go for bigger. So remember, if you go for large scale batteries, I think with the university is very difficult because the reason is that safety issue, and you have to prepare more materials or more on industrial research. So what usually as electronic engineering point of either you can prepare as a kind cell, or you can buy some commercially like 1860 cell. Try to concentrate what is your for example, you're designing the in situ sensor, for example, how to monitor thermal management, everything, or you want to design a sensor based technology. So that is a nice contribution, especially for the electrical engineering point of view, and especially fast charging aspect, and then problem is the safety limit, etc. I'm going to touch up in the next slide. So in fact, I want to maybe what is my talk to be simple. So it's very important try to understand the basics. As I mentioned that materials are same if you use with hybrid vehicles or your mobile phones or kind cell. Only the designs are different. So usually in a typical battery or whatever mobile EV or mobile phones, it contains a positive electrode and there is a negative electrode, and there is a separator to avoid short circuit, and there will be electrolyte. So it's very important. So electrolyte is a medium to move the ions from one side to another side. Usually it should be liquid, or sometimes people are using a polymer based electrolyte, and separator is the purpose to avoid the short circuit. Otherwise, so remember, so these people can use different type of electrolyte, either liquid electrolytes, or there is extensive research is going on. Since it's not specialized one, I'm not touching more on this type of the real. Okay, so you have to remember any cathode should be either sodium or anything. It should be lithium containing lithium or layered containing compounds. So here what will happen? Here is the cobalt is in 3 plus. During charge, oxidation will occur 3 plus to 4 plus. So it is simple high school electrochemistry is like a charge means oxidation, discharge means reduction. So that is enough for the time being. And usually negative electrode people use the sodium or lithium metal if you use the sodium batteries, or people use it in terms of graphite, carbon, and some Li40 for metal oxide, etc. So charge I mentioned that is nothing but oxidation, analytic scan, and sometimes if you go for electrical engineers, they call a state of charge means how much percentage of charge like that way, discharge reduction, negative current, etc., etc. So this is a principle of lithium-ion battery. As I mentioned that your battery containing the three components is a cathode. So what will happen is that during the charge, the lithium move from the one side to another side. So here positive to negative, where the electron will pass to the external circuit. During discharge, reverse reaction is occurring. It means lithium will go back to the original state. So what will happen here, cobalt, during charge 3 plus to 4 plus means oxidation will occur. So as a consequence, we will get the color the current versus voltage potentials. We will get a peak, is called as the oxidation peak. Again, during discharge, reverse reaction is occurring. That's why I call it the reduction peak. In summary, so what will happen during charge? You will get a plateau. So you can see, for example, you can see the nearly 3.5, 3.7, nearly 4.1 volts. So good battery. So voltage nothing but difference between the charge minus discharge voltage. For example, suppose so you can see here 3.2 volts minus 0.25, or some cases you may see that nearly 4 volts minus zero point 0.3 volts. That's why it is like, suppose if it is a layered compound, so your battery become 3.7. So that's why sometimes you can see this 3.7, or you have some other battery chemistry. If it is 3 volts or 3.2, then it becomes lithium iron phosphate, or different type of the materials are there. So that way you will get some idea, especially while checking the battery pack in the. And so that is the way, just you will get some fundamentals by using this, by learning this type of the concept. So what I have discussed, since people are not able to, since the previous slide was a little bit busy slide, the same thing I'm going to do it in some like little animation. So as I told, the cathode is like that way. There is a lithium move from one side to another side. So what will happen is that, for example, 0.5 lithium is removing. So that's why we need a charger. Again, so discharge, what is happening is that all the lithium is going from the negative electrodes, will come back to the original state. You can see here, again, lithium will go back to the original state. That's why we call it a rechargeable battery. The rechargeable means it is nothing but oxidation and discharge. So that's why. So remember that during the, although the materials are not 100% zero strain, sometimes during long-term cycling, where for example 10 years, 15 years, so there is a small lithium concentrate structural modification occurs. That's why you will see small battery failure, what they call capacity is fading like that way, with respect to the using for the long-term cycling. So, so in fact, you know that is any grid or smart materials, we broadly classify in four type of mechanisms. Among more popular is a lithium intercalation, the intercalation reactions. Here, only with we play with one or two lithiums, and we don't see any huge volume variation. For example, once materials, for example, here there is a alloy-based materials. There is a contraction will occurs once you discharge the batteries, and the contraction expansion as a consequence you may get what they call as a capacity fading depending on for long-term cycling. And anyway, these are the different type of nano size approach with the different oxides. Since it's not a specialized one, I think I want you to understand. I think the simple concept is that oxidation reduction that will be sufficient for the time being. So now regarding the material issues, as you told that functional materials are needed, especially either you working with a sensor or any material, it should be low cost, and especially sometimes you now we call it sometimes nanomaterials means 100 to 1 to 100 nanometer submicron size, especially for example different approaches have been adopted in the, for example your electrical engineers, I think you people are mainly focusing about shapes, and then for example metamaterial, or for example you can see here. So anyway, nanomaterial slightly different when compared to the bulk material, especially space specific. For example, for a specific application, for example, antenna or metamaterials application, I think people want the material should be what they call as, for example, silicon with a proper structures is needed for the depending on applications. Or for example, nanolithography, or for example, MEMS applications, we need a proper materials in advanced technology is needed to prepare. So in summary, if any researcher pick up what type of applications are there, depending on you select the material and what type of the available facility and what is their specialty as your boss or your professor, what is their specialty. In fact, you remember one person cannot do everything. For example, you cannot synthesize. It is very difficult depending on expertise. So that's why based on the capabilities, you decide what type of properties you want to do. Accordingly, then select a candidate. In fact, we cannot do as any PhD student or any student, you cannot do too many candidates within a 3 years or 2 years. So at least we can select the candidate. And again, what is your purpose? You want to study the structures or shapes. Accordingly, you can design the material. Again, at the end, processing the material is very important depending on the especially size and shape of the functional properties. Here, the smart material processing and characterization techniques I'm going to discuss. You see the periodic table. In fact, many materials, I think some few materials are very useful. For example, PN junction, some particular materials are very useful. Or, for example, you want a hard coating, if you want titanium nitride, we need titanium nitrogen. Or if you want to be silicon nitride or osmium oxide, or with a special applications, especially for you want to prepare, depending on that one, we need a, although we need don't need any complex oxide, depend, for example, some superconducting oxide, like yttrium, barium oxides. In fact, those are all things people will prepare. Either you can make a target, for example, a pellet, and you prepared in the form of thin films with a desired shape and size. So that is the way what they call as electrical and communication engineers you're going to concentrate. In fact, there are the two options. Since the energy people, for example, people they can adopt bulk chemical method. I'll tell you what is the specialty of this one. So advantage of this one is you can prepare a large scale, and then these are oxides. You want to prepare in a batteries and energy storage. It is in terms of tons of the quantity they have to prepare. So you have to think about the material should be very simple. Suppose another application, another side you can see physical method. For example, you want information and telecommunication applications, you have to look for thin films. Why thin films? Because you are looking for very miniaturized devices. A device should be very small, and make sure that with a specialized application, with a specialized, almost like what they call the angstrom. For example, you can see the atomic layer deposition. People can deposit by using osmium oxide 3 nanometer and silicon oxynitride with 1 nanometer, and on silicon n-type silicon substrate. So what I'm telling you that it is like it depends on the application. We suppose you want to prepare atomic layer, we don't have any ALD atomic layer deposition. We cannot use this, for example, 1 nanometer technique. We cannot. It is very difficult to control with 1 nanometer by chemical method. So sometimes we hear what I'm suggesting is that since you are the electrical engineer, so you need a specific instrument to do with a particular application. That's why sometimes I know that you want to make a little bit molecular beam epoxy. In fact, very expensive. It's a little bit difficult to do what I desired. For example, you may not get very. We know that this type of technology or the performance depends on how you're making a proper, what they call as smart device. That's why if you make a smart device with proper contact or proper characterization one, I think we will get the better performance. Since so if the facility is not there, and then it is difficult to do. I know that sometimes the expensive equipment like MB, molecular beam epoxy, they're all things more expensive, and it is not so easy. Suppose learning the whole process, it will take nearly more than 1 year, 1 year. So at the end, second year you have to optimize the things, and then third year again go back to look into the real properties. It will take some time. The thin films it is a little bit more time according to my experience. Since I did my PhD with one materials, it took me more than 3 years to optimize to do so many things. Okay. So in summary, so either maybe if the RF sputtering is a very long, large scale, is a more less expensive. I think is available, including all your universities, like your this very useful, and PLD. So it depends on the which area you want to focus. And for example, molecular beam epoxy is a little bit more expensive, and plasma enhanced CVD. It depends on really, in fact, large scale application depends on specific. And nano imprint lithography is also very good technique. Nowadays, recently, in fact, in NUS also, I've seen some synchrotron technique people they use for the making the metamaterial using nano imprint. They think that using the technique, they're able to get a specific application with a more precise way. So they need to prefer what they call as the exact shapes you want, which are the dimensions. Usual way is that they put a particular mask accordingly which area they want to either coat. You can do that one. Another approach is electrode deposition, because it's very important for some particular large area. You want to be particular. Yeah, for example, copper contact, you use the copper electrode depositions, and for example, evaporation techniques, and then nowadays 3D printing, either polymers or ceramic material. We can use this type of the technology. Again, the ceramic material is a very important criteria. In fact, suppose you want to be, for example, what they call as a cooling system, sometimes some particular application, plasma sintering, it is called as additive manufacturing. In fact, people want to prepare, for example, so you can use a spark plasma sintering or hot press. It's not this. So this technique to what they call make a sintered pellet, make sure that what they mechanical, for example, alloys want to be carbon-based composites they want to prepare by using this approach. So overall summary is that since you are electrical communication engineer, maybe more useful methods are this one. Although these techniques are more on the battery people, still I don't have much time. Still, if time permits, I'm going to touch up some few example. What is the meaning of that one? So I'm going to focus on the at least one method. What is the meaning of energy, etc., etc. So next one is very important. Once you make this device or before device, you have to see you have proper phase or proper composition or not. So best way that as a crystallographer, I think we do XRD. In fact, for your case, if it's a copper metal or silicon metal, that usually will get there is not a problem. Or silicon oxide, you can get a different type of phases. That's why X-ray is very useful nowadays. Very depth resolution. We can see in a particular area with a particular phase. Suppose, for example, you're doing sintering or layer by layer, we can check by using what I call glancing angle XRD. With it, depending on thin film geometry, a lot of options are there. And especially for lithium, we work in neutron diffraction, sometimes X-ray diffraction. They're all the fancy techniques. If you're depending on your research, you can do. So again, it's very important since you work with, for example, integrated circuits, thin films. My experience, Rutherford backscattering spectroscopy is a very useful technique to know the composition thickness or to see the interfaces. For example, what is going to happening? Your material is diffused into the substrate. For example, you sintered silicon substrate. So all your ions are going to be inside the diffused into the substrate. This is very useful tool. And we can check the Auger electron spectroscopy to see the composition homogeneity. In fact, these are the two important techniques may be useful for you. Anyway, at the usual practice is that most of the electrical engineers, I think since the facility is not available, I think what people will do is that so they will go for a particular method. They try to prepare and look for the, for example, terahertz or what is the IV characteristics. Based on the good response, they can publish. Anyway, depending on the journals. So this is the way usually you have to do. So still, without this one also, so we have some other, since you people have characteristic criteria depending on what type of their IB response is to get, and depending on that one, people can do. So again, since we are the battery, we need a fast charge. I'll tell you example what is meaning of impedance analyzer. So is the impedance analyzer here? I think we work with some 36 megahertz to 3 millihertz. I think you people are working with some electronic terahertz range also we needed, okay? And sometimes like microscopy techniques are needed. So these are the various bulk nanomaterials you want to design. In fact, these are all things and in terms of the energy storage, and some material may be useful not for all the material. So in summary, we need a fancy techniques. As I told that X-ray is a very useful technique to either you do with a battery engineer or if you have a ceramic material, for example, thin films, you heat and cool what type of phase transformation you can see. And we can do some Raman spectroscopy. It is, for example, your graphene or coating anything, etc. I can do. And microscopy and some fancy NMR techniques you can do. So fast chargers is a very big, interesting topic. In fact, nowadays, if you see that hybrid vehicle, wherever the good infrastructure, I think they put a charger. Only you see the cable. So usually there is a electronic circuit inside the big setup. So what it will do is that so it will monitor the fix the voltage. It will tell okay the particular charge go to this voltage, go to this voltage. It will tell the particular cutoff voltage, and also there is a safety limit. So, for example, in a battery, instead of go to higher voltage, so you to remember the if you limit reach the safety limit, then again your battery will explode. That's why it's very important. Safety is a very big issue. That's why each the vertical chargers it will tell that okay go to particular voltage and stop, and it will monitor the current, and so this way it is advantage. So again, so there is a huge if you go for grid vehicles or V2G solar inverter, so many things. I think fast chargers are will play. In fact, this is a all role belongs to especially your electrical engineers. So you can do very interesting discovery. Anyway, since in addition to the fast charging, I think still as a material engineer, I think people look for some new materials should be very fastly charge the things. So that's why some problem with not only chargers now the problem of these material inherent property of material, and that's why nowadays we have to look for the different ways of improving the what they call as nano conductivity, nano channels, like etc. etc. We are trying to do. So in summary, capacity is nothing but how much time taken from this from 3 to 5 volts, 4.5 volts, and multiplied by current. and divided by mass of the materials. That way we call as the capacity, and it is very useful in order to evaluate energy density, power density of the battery. So, for example, simple term already I discussed about energy density is nothing but voltage of cell is the cathode minus anode. We'll get a nominal voltage multiplied by capacity rating. Usually, if it is 18650, they will get amp hour divided by battery weight. For example, if you 18650 cell 3.6 voltage rating and 3 amps, so then 45 gram weight, nearly 240 watt hours. So that's why these materials are very, so that's why we cannot replace this lithium battery technology, other one, because almost 240 kilowatt hour gram is ideal for the electric vehicles. That's why, so if you ask any other materials, so your voltage not matching, so we cannot be really useful for the applications. So another is power density. Again, the power energy density is nothing but voltage into capacitor by weight. So power density is nothing but same voltage multiplied by current. Okay, so that is called a power density by E by liter or kilogram. So what we get the information based on the galvanostatic cycling, we can get small information, and based on that one we can calculate the capacity, how much time multiplied by current, and then this gives capacity. And theoretically also you can calculate based on the number of lithium and Faraday's constant, divided by molecular weight of material, we can calculate. And also we can calculate Coulombic efficiency, then we discharge minus charge, and 100 minus will get Coulombic efficiency. And irreversible capacity is very important. Once it charge, usually initially some batteries you may get higher ICL. I think this is not really good. That's why in usually in a commercial battery they will do initially few cycle they format before sending the batteries. That is the way quality control. That's why sometimes depending on company to company, some companies have good quality control. That's why they have lost longer time, and some battery company they don't have proper quality control, so we will not. And also it depends on material and what type of technology they are using. Again, these are C rate and how much I told you that we people want to be, means 5C means 12 minutes, and 1C means 1 hour, 0.1C means 10 hours. So 5C, like that way you can calculate the C rate. So impedance analyzer is one of the equipment people want to study. In fact, this technique is very useful if you work with terahertz material, or you want to see what type is happening. For example, so usually we work in the 36 megahertz to 3 millihertz frequency and AC amplitude. We see what is going to happening with respect to scan with from the high frequency to low frequency. We'll get a different, for example, in a battery during before cycling, we'll get a single semicircle. After charging, we can see different type of data information. Since it is not a really specialized conference, so still I am telling that since we are a physicist, we can do some modeling. So simple is one resistor, capacitor, or we call it constant phase element. Or sometimes if you are electrical engineer, sometimes if you do the cables, you can put inductor or resistor in a different way, either capacitor. Idea here is that only just is what the symbols or convention will be very different depending on the expertise. Again, the modeling almost same. So usual way is that so best way. So this impedance spectroscopy is very useful to know the what is going to be mechanism, especially for example if you are electrical engineer. Suppose another way is that your circuit is good or not. Also you can tell very clearly. For example, you have bad circuit in the sense that bad contact, so you will get very noise is very huge noise. So clearly indicate that this device is not good. That's why quality control. That's why so this technology may be useful. So if you people want to see the particle kinetics and aging, for battery it's very complex. The charge transfer and bulk and resistance, charge transfer, bulk and Warburg, etc. So as I told that again, it is very complex depending on subject, really what you're looking. So we can do lot of complex modeling. You can do different type of the what they call resistor, capacitor, and inductor. Different way you can do depending on which what you're looking. So it's very important. What is the what you call fundamental understanding with respect to voltage, charge, and cycle number. So this is very important for to try to understand. So and then if you go for the what they call electrical engineers or the physicists or chemists, you have to understand very carefully with this type of the models. So it depends. For example, different type of the model. Again, the same resistor. If you use the particular commercial Panasonic battery, so here you can see depending on the system to system, we can see different type of response. Again, we can do modeling and we can fit what type of resistance. based on capacitance you can calculate. Okay, so again, IV curve is, in fact, long back I discussed. Sometimes I go and talk there, and people ask me what is IV. So that's why it's very important. IV is a electrochemistry batteries, what we call as a reversible peaks, called as oxidation and reduction. So sometimes you, especially for example, this is a IV curves with respect to the WST thin films. You can see the current density versus voltage. So different way of plotting. For example, solar cells, this is voltage versus current density you can do. So since it's a battery one, so here it will give the information about the oxidation and reduction peaks. So this is the way. So just I want you to know that, for example, battery cyclic what IV curve is nothing but it will give the information about the oxidation and reduction potential of the good battery. So best way that any, if your battery is working very well or good thing, the reversible battery means you have to get a positive and negative current, clearly indicate that. So this is the reversible way. In case if you don't see any negative current, clearly indicate that this battery is called irreversible. And anyway, we can do a lot of things. For example, you can understand what type of diffusion coefficients way, like that way. So anyway, and regarding the smart materials for batteries are concerned, so usually you can there is a lot of materials are there. Since I don't have much time to discuss, I will going to summarize one or two example. Then I'm going for some other topics will be useful for your research. The smart materials for batteries, mainly you can see there is a problem with this limit. Only this limit we cannot go higher, because that's why we need a smart material, new materials. You to, especially you can go up to more than 5 volts or higher capacity, 2 to 3 lithium will go, there is good. And graphite and lot of the oxides are there. So these are the future generation people are using for the presently. I think nowadays people are, what they are doing is that they're not worrying about the new, especially for company or electric vehicle. So they're talking about the commercial available material, and they're optimizing, take existing material, try to improve the what they call as fabrication technology, cell design, depending on the requirement, and then depending on the what they call energy density. People always doing what they playing with respect to the different designs or the electrode engineering, etc. So these are the different type of the compounds, and there are the limitation and etc. So one example I'm going to discuss why this material is very popular, because almost reasonably nearly 156, and expected with the vanadium 3 plus to 4 plus. Actually is here it has to oxidize, that's why we are able to get a 3 plus to 4 plus lux potential, and a reasonably good thermal stability when compared to the lithium iron phosphate. And we know that phosphorus oxygen bonds are very strong when compared to the metal oxygen bond. So we try to prepare the sample by using some approach like for the chemical methods. Here advantage, we want to prepare in bulk tons of the quantity, that's why chemical method very useful. So once you do this one, this is the way you make a device. For example, you any battery, or so in a lab scale, you can take with a small beaker. You take this one, put 70, 58%. These are all the way of making the slurry, and coat it on your cathode means aluminum foil, anode is the copper foil. Coat the materials and this one, and finally roll it in order to make a good contact. And finally, you press into coin cell with 16 or you want to be big pouch cell, depending on that, you can cut it, and finally pass it in a vacuum oven so it dry the thing, and put it in the glove box. It's very important, glove box, the argon filled glove box. So really, for example, large scale industry, I think they use a dry room, so usually, in fact, for any university, I think the glove box is needed to do the research. So again, you can make a coin cell like this way, for example. So you put bottom cap, your material like that way, and put a separator, either lithium or metal, and finally top cap, we can get a button cell like this way. Remember, the cell is good. You can do performance, what type of studies you want to do. I told you that you want to be using this setup, charge fast charges or charges. You can do, you can monitor the voltage function of time. From that, you can calculate the capacity. So almost like this battery is run for near 6 months, reasonably good stability. If it is bad, means we are going to die within 50 cycle, indicate this material is not really good. And interestingly, this vanadium contain compound nearly 4.1 volts. As I told you that higher voltage, it means that higher energy density. So that is good for the what they call electrical applications or high energy density applications. Again, we can do with higher current rate, etc. And these are the reversible charge discharge. They call IV curves, what you call as electrical engineers. So, and we can do some complex impedance. So here you can see with respect to the voltage and its cycle number, we see what is going to happening with respect to the cycle number, and we check the how the material is degraded or not. So this is the way for the long-term cycling, etc. So in summary, so why we are famous, because this compared to this your iron phosphate and other commercial vanadium containing compounds are reasonably good, because so here 3.2 volt will get nearly 4 volt, nearly zero point 0.5 volts improvement in the capacity. Automatically will get more energy density when compared to the lithium iron phosphate. That's why this is the way you want to design any new material or anything should be higher energy density state. So another example, new materials, since we look for new materials, so is very important. Also, we took some these are new compounds we even reported. So in terms of the voltage wise, we're very happy. Nearly 4.1 volt we're getting. At the end, we may ask you that although capacity is not very high, that's why sometimes, although people will climb very high capacity, sometimes so we don't, either voltage is not matching. So here voltage is very good. Only problem, capacity was low. So that's why for especially for long term large scale up are very good application. Nearly the capacity is to go to nearly 150. So then it is really good for real applications. So it's very important nowadays. I think people are due to the what the lithium is a little bit less, more expensive, and sodium is more abundant. That's why they're looking for sodium is the approach. Again, there is a problem, sir. It is not like sodium is going to be still, as academic researcher all over the world they're focusing with respect to sodium is an alternative things. Again, it's because again they remember sodium compounds are hygroscopic. It's not so easy to handle when compared to the lithium. And one simple example, it is the vanadium containing compound, almost same structure, sodium by lithium. Nearly here you get 4.2 volts, you'll get nearly 3.5. That's why voltage will come down automatically, energy density. And for the stationary application, for example, grid, for them, the voltage, since big, little bit bulky, also no problem. So that's why, depending on the application, these are an alternative approach people are doing. I think these are the samples we can prepare since I don't have much time. As the engineering point of view, so another these are Nesicon type structures. So we've been some carbon coating approach. So reasonably good with a nice conducting carbon coating, reasonably nearly 10 C means fast current rate we can go. And the reason is that we check with impedance again. What they call an impedance analyzer is very useful to see the resistance. So because of nice carbon coating, we'll get a lesser resistance when compared to the other material. And anyway, you can see the capacity variation, etc. Since I don't have much time, I can, in fact, people can do Raman, etc. So safety is a big issue. In fact, as you saw that sometimes people are climbing it due to the safety. So either due to the problem of the either malfunction of the electronic circuit, either you electronic engineer did some mistake with what they call as a electronic circuit, or there is a problem, for example, in future with hybrid electric vehicles. I think there is a what they call a huge. Suppose you want to respond this your EV battery to, there is a big panel. So there is a integration, but it means there is a what they call as electronics. All this one should be very automatic. Suppose if you do small mistake, either problem with your material, or either due to the electrolyte, it will catch fire. That's why, and also due to that's why nowadays people recently looking for you to replace the electrolyte by liquid electrolyte by solid electrolyte, or there is a problem with this what they call as during the charges. They're going to check that one in a different way. So one way is that we thought it is like in situ with the X-ray crystallography. You can tell clearly with the real-time monitoring with the battery. This is the beryllium window. You can put with this battery, small battery. So doing the XRD is going to record with respect to doing charge discharge, and we can monitor the signal, for example, during charge and discharge with respect to potential. As you can see clearly, so the XRD the peak. For example, anyway, I don't have much time to discuss what is the really X-ray looks like. It is like when diffraction is a phenomenon, when X-ray is incident on your any material, diffraction will occurs. So since you are a medical engineer, they use the X-ray for imaging purpose. As a metallurgist or materials engineers, use it for the phase to see what type of phase is there, how to identify if it is pure or not impure. That way, very useful. So usually the cell, the what they call it lower angle, it means that there is a expansion contraction occurs. That's why there is a in a reality, although you get high capacity, they will stop nearly 4.3 volts in a commercial cell. They will not go to higher voltage. It's okay. So that's why. So there is a limit for the each materials depending on safety limit. That's why we have to see the chemistry, what is going to happening, or physics or electronical engineering, etc. Anyway, these are the more things of chemistry I'm going to skip, and sometimes you can do some fancy techniques like NMR, etc., etc. So another one is, if you want to use a smart cities, I think we need a smart windows or smart vehicle, what they call as a smart glass. Or for example, if you use a solar cell, we need a smart. Okay. So although I don't claim that TiO2 we can replace the silicon solar cell, still I think this I'm telling this in terms of academic research. Still, silicon is a more famous because silicon is very what they call as a very hard, and technology already established, and the stability wise very really good. So since academic research, in fact, TiO2 is well known. People are using for sunscreen as a coating material, as well as the paint industry, as well as, for example, smart glass, etc. And you can prepare by either by chemical approach, or you can do, if you want to use smart glass, people they can use RF sputtering, use the titanium target, and pass with oxygen gas to get a titanium dioxide thin films. Since is a battery or energy storage or anything, we need a bulk material, like in a kilogram the quantity. Material should be simple, and it should be, you can prepare in a large scale. That's why we used need a chemical methods, and we check with respect how the X-ray looks like, the single phase or not, and we can do some what they call it based on that one. If it is nano size, surface area is going to higher, and the crystallite size is going to be lower, and keep on increasing with respect to eating this sample. In fact, these are all the things you learn with a simple materials engineering course, etc. You can do again TM to see what is the particle size, etc. So this is one example. If you go for nano size to micron size, how the performance is going to be vary, etc. So again, the solar cells. In fact, the solar cells, the already technology is known, so I don't need to thin film solar cell, the crystalline silicon solar cells. Again, so these are all the limitations, and each things is there. I don't have much time to discuss. Again, as a new academic researcher, I think people are looking for studying in terms of organic and dye-sensitized, and so perovskite is a new area people are concentrating. So one example, usually should be dye-sensitized, so make sure that band gap should be nearly 3.1 or 3.2 depending on the like TiO2. TiO2 is the most commonly people are using because so the band gap is optimum, and also so people have been look for the various electrolyte combination, etc. And then so advantage here we need a porous sample. It should be more so the electrolyte has to penetrate. We are able to get a good performance. This is one example. If you go for commercial TiO2 with 50 meter square surface area with 200 meters prepared by ourselves, and we are able to get slight improvement. It's not like huge improvement, still there is a small improvement is there. And also we checked with some of the nanofibers by using the titanium. These are all the semiconducting materials, so we've been checked. And recently the perovskite solar cells, in fact there is a huge interest. Again, remember, you want to make a device, you can see they're all electrical engineering. We want to be say a quick flexible device. Lot of things I think people can do. And then again, depending on the facilities, you can do multi layers with a available facility, roll to roll approach you can do by using this material. Again, I think each technology will limitations are there. In fact, these are toxic, and stability. Lot of challenges are there in this type of the area. So I think one slide is very important. If you go, since you are the mechanical engineer, so are the electrical engineer, it's very important to understand what I do, what is, how do you know how to get a thin films in a different technique. One by chemical vapor deposition techniques. Here, the reactant gases are introduced in the chamber. For example, you take a titanium metal, react with oxygen, will get a titanium oxide films. Or you want to do titanium nitride, or if you do titanium target and nitrogen gas is to pass through, you get titanium nitride. Or you want to be tantalum nitride, you can put respective one, or boron nitride. Accordingly, depending on your requirement, or for example, osmium oxide you want to prepare, you take a osmium target and oxygen one. So that way we can do the RF, so what they call as chemical vapor, sorry, with the chemical vapor deposition techniques here, uh, physical vapor, what I discussed, chemical vapor deposition technique is like the precursor should be volatile, in the sense they use some organic, like a metal organic precursor, so it should be volatile. So what will happen? They prepare a precursor at a particular sample, they'll evaporate it and pass the gas to get a respective thin film. That's why chemical vapor deposition. Again, they can go to different varieties, either by CBD, pressure, plasma, different. In fact, these are all industrially demonstrated. So many things. especially you want to be high dielectric material, silicon or silicon nitride. By using this approach, people in don't develop. Again, physical vapor deposition technique. Again, already here we need a. I want to prepare thin films. We need a advantage of physical vapor deposition technique is that no toxic gas. Here, if you do silicon nitride, silane, so we need a toxic hydrogen. These are the toxic gases emission. Here we don't see that much of the problem. Again, advantage of physical vapor, we can get a large scale. So suppose, for example, your ICs integrated circuits, we need to be specific. For example, ALD, we want to a particular layer, for example, nanometer coating layer is needed. So particular application we need ALD and PLD also particular areas they want to sputter. So that's why some special or molecular beam epitaxy. So this technique means we want to usually epitaxy is nothing but a particular for example, silicon or magnesium or some particular stanchion, some substrates, and that one they can grow the thin films, so they can study. So in summary, depending on applications, you have to optimize thickness is very important. You have to see which applications are there, according to thickness should be there, so we don't want too thick films. And composition, it means composition means what type of this one, understanding the electronic and what type of the, for example, optical properties if you want to better. And surface interface is very important to understand what they call as the effect, and mechanical properties are needed. So in summary, I think these are the slides really useful, especially for electronic engineer, those working with MEMS technology or Cosmos technology, etc. So one example is thin films by RF sputtering. So you can play with respect to power, total pressure, distance, target substrate, oxygen or nitrogen or an ammonia, any partial pressure, and you can play with the distance, etc. At the end, composition, deposition rate. The deposition rate is a very important one, and morphology, structure, etc. Again, this is a sputtering unit. If you want to glow box, advantage is that you can, if your samples are hygroscopic, you can use this setup to prepare the material. So remember, suppose if you people are working with, for example, so multi-target, for example, 2 to 3 elements are there. What people will do is that exactly you try to put instead of one target here, the bottom, they put, for example, titanium target, chromium target, or chromium metal target, or any which are the metals you want multi-target, they can put it accordingly. So for example, you want a particular layer by layer growth, they can do. So whichever the requirement depending on thickness. Remember, there are all things it will take some, because since each industry there is a what they call as the process parameter they've optimized, they spend years together, and the only thing is that just we depending on requirement and people are doing that one. In fact, there are all sometimes each recipes, there is each industry their own patented issue. That's why sometimes it is all this one. You have to suppose you want to be lab scale, any technology or anything, at least we need more time to optimize the specific thickness. So many things you have to optimize. It's not so easy sometimes doing that real experiments with thin films. You need with really lot of time. For example, this RF sputtering is not a straightforward. You have to wait for some time to reach a vacuum with a particular vacuum to get a good deposition rate. There are all things taken to consideration. Again, uh, so one example is, for example, is microelectronic application. For example, the idea is that I think long back, not much success. So our group in France, they used to looking for the microbattery coupled with a smart card. That is our objective. So long back, I think more than 50 years back, they started. So there is a huge challenges, especially here, is that there are a lot of complicated chemistry. So remember, usually there is a thin film with cathode, thin layer of cathode, electrolyte, anode, and there is a protective layer. They're all the whole battery is 10 micrometer. So anyway, this is very good for micro applications. The problem with these batteries, for example, these are solids. Usually we need a amorphous material will not work. It should be crystalline. It's crystallized. Okay. So this crystal, you want to be crystallized these films, we have to go to high temperature. So automatically, what will happen? Sometimes it may react with this one, or sometimes you may not get a required composition. That's why, so a little bit challenge in this one. Still there is a lot of interest on this one. So it is not like what they call Moore's law here. Somehow this the technology, I think the lot of effort has been done with my previous boss. I think not only some Oak Ridge National Labs, especially micro batteries used for the MEMS applications. So again, the same technique, people want to be electrochromics. Suppose you can deposit in what they call ITO substrate, indium tin oxide substrate, and you can deposit tungsten oxide, and you can do something like basic color smart windows, etc. ECD. Again, you want to use a polymer. Anyway, so many things people can use different approaches for the smart windows. I think this slide I wanted to tell because of different reason. So we know that RBS is the one useful technique. For example, thin film. Not many people can access the Van de Graaff generator. I think India also we have to go either Kalpakam or near in Bhopal. So there is the indoor or somewhere in Calcutta. Some 3-4 places they have facilities. So usually Rutherford backscattering spectroscopy. So he's a British physicist. So he discovered Rutherford backscattering when he was in McGill University in Montreal, Canada. In fact, in the physics department. So here, idea here is that when incident beam of helium or protons are incident, we can get different type of transfer, either nuclear reactions, what they call backscattered electrons. This one backscattered electrons is called as a RBS, Rutherford backscattering spectroscopy. Also another thing like FIXI means the gamma ray. For medical applications, people use called FIXI, the proton induced gamma spectroscopy like that way. So here the thin film is nothing but when helium beam is hits on your, for example, in thin films. So what will depending on the energy, depending on thickness, there is a kinetic energy E1 and E2. So what will happens is that depending on the atomic mass, for example, here the higher atomic number mass comes first, followed by lower atomic number. So it is nothing but so it is a typical RBS spectra, the simulated spectra by using nickel, vanadium. So here is that advantage is that we know the what type of composition or is there any impurity. So it is the best technique, and also we can see with this nitric carbon and oxygen. You can see that higher atomic number first, or what they call the mass number, atomic weight. So another example, if it's zinc oxide films, if you deposit on silicon substrate, because substrate come followed by oxygen, is a carbon substrate like that. Okay, and also is a thin film and thick film, depending on that. And also very important information. For example, if people are working with the Cosmos, so they call hafnium oxide 3 nanometer and silicon oxygenated 1 nanometer silicon substrate. I think these are only one technique based on so the best technique to get high resolution, good information about the composition. You can see the hafnium. So expected composition, we can do simulation by using the rump or different options are there. Again, with RBS is a literature studies with I think this with with NUS with SIBA laboratory. What reason is that I think this technology I think with Micron RBS I think they studied the commercial they call printed head with for example silicon carbide silicon nitride. So this composition we can check by using this approach. So still the thin films you want to see, for example, during annealing and heating, for example, you do any micromechanical device while heating anything, I think this RBS technology is very useful. Also, we check with some cobalt nitride and with a simple sputtering cobalt. I told you the cobalt, metal, and nitrogen gas, and we can get a either you do with X-ray. X-ray also we're able to get a center expected cobalt nitride films, and with respect to the thin film by using the RBS approach, we can do. So since my time is so and also we can do some bulk material etc. So for example, you want to prepare some nitrates or anything like for example boron nitrates or some particular applications you need a nitrogen containing hard material, for example chromium, vanadium nitride. So best way is that you prepare a respective oxides, or I know thin films is the best way you can go. Otherwise, you want to be large scale, you can use a simple tube furnace. You pass the respective oxide with ammonia gas, we can get it. Again, remember this is a bulk one. So you want to again integrate or miniaturize one. So we need another technique, or you can take this target, or we have to make a palette in a different way is needed. So another technique is, for example, is electron beam lithography. In fact, this technique is very useful to process, for example, fabricating silicon imprinting templates in a T-shaped target. So again, so again, it is like depending on the design or shapes, your design is like okay, different type of steps. For example, E-beam lithography. So the first is, for example, chromium, different type of the metals, and you can do ion beam, reactive ion beam etching, and different way steps are there. In fact, these are all things, for example, you can do, these are the standard E-beam lithography technique. And also we can do some synchrotron technique also is more resolution. I think for especially for the wave, what they call the metamaterial or wave grating applications, I think we may need a specific what they call as a wavelength. So for that case, I think we need a depending on the application, we need different type of the structure for the different type of the applications. So these are with a plasma CVD. With the plasma CVD, we can get different type of the either silicon nitride or silicon carbide type of films. So you can do for the sensor since my time is a little bit going up, I think sensor is not much time. Since I want quickly, I'm going to. I think in a smart city, sensor is also will play an important role. So what it will do, sensor is it will especially for use automatic applications or food, especially in a smart city. It's, because it has such a sense, so for example, people are putting for the dustbin or garbage. In a sensor, it will detect, for example, it is very dirty, and you get the sensor signal to your mobile phone or anything. Okay, something is happening, so we want to be a smart sensor. Also, anyway, sensor people can use it for agriculture and especially medical applications, for example, glucose sensing, etc., and water treatment, environmental and industrial safety, and petrochemical, steel, and aerospace industry. So, in the sense that these are the various type of this smart material people can use in case semiconducting sensor. Because use, I told you that titanium dioxide. Also, I discussed this when you can use sensor tin, because these are all what the white containing semiconducting material, because the band gap is around 3.2 something like that. So we can sense different type of the gases, etc. So another one is very important one is the yttrium stabilized zirconium oxide is the proton conductor. So usually there are all these and yttrium stabilized beta alumina. These are all these things sensors are using for what they call as others. So platinum, aluminum, platinum wire. In fact, there are all the sensors are needed for, especially you want to be smart city or anything. So this sensor design also needed for the applications. Since I don't have much time, so how to get the resistance of, you can do solid state type of gas sensor, either potentiometric, amperometric, and resistive and impedance. So anyway, so we can calculate how the resistance with before air and then RC and with respect to see how it is going to be. So these are all the things mainly depends upon. Suppose, for example, if you go for miniaturized device, I think we need a little bit a lot of expertise with your electrical engineering background, so that you want to be if you want to prepare thin films and particular things, we need a more specific applications where to what they call as the way to prepare the material accordingly. So classification of solid state gas, there are type 1, type 2, type through. So in fact here, I think in summary, I can tell that material will play an important role. So there are the different type of the mechanism. These are all things, remember this, for example, they can use, these are all the layer by layer. Either you can do, usually these are things people can demonstrate by using the thick material. Still for a practical application, they're all the thin films technology is very useful to make all these materials for sensor applications. I think one example, so these oxygen automobile exhaust sensor, I think they're all commercialized. So you can see the small heating element. So it contains a platinum electrode and it stabilized this ceramic electrolyte. So that's why you can use it for the sensing the uh, automobile exhaust applications. So you can see depending on the concentration it will tell. So anyway, these are the CO2 sensor is a very important one. In fact, and then uh, for example, one example is a ceramic based electrolyte. So you can make an oxide, it's a silver paste and garnet type of material. We can we can use this type of sensor based material. I think these are the key issues: durability, sensitivity, instability, and selectivity. It's very important. In fact, we cannot use the same sensor for the whole application. For example, in a smart building is there. So suppose same sensor has to visualize everything has to do. In fact, the same thing way. So in any building, in any smart building, they have it will detect how the people are coming. So that's why I say one sensor we cannot use it for the all. So like same problem with we want a sensor should be multi-elements or multi-gas sensitive techniques are needed. In fact, those are the things is going on with the different approaches. So semiconducting, either you can do N-type, P-type, and composite sensors also we can do. Okay, so I think I have another, now is 11:15 means 11:15. We have another 2 minutes or 3 minutes I'm going to summarize. So the ceramic electrolyte, due to time limitations, so usually ceramic electrolyte we want to be high conductivity. These are the major issue. So and the material should be because if you can, it should be while pressing the sintering pellet, should be material should be no reactives. These are the major problems we are facing now. So these are the different type of the solid electrolytes are there. So there is a lot of challenges because problem is these are the ceramic electrolytes are high temperature sintering is needed. So these are a little bit challenges. And other materials, in fact, these are quickly I'll go through. In fact, these are all the some people are working with the graphene by especially chemist or the materials engineer. Either you can do graphene, for example, fill air graphene. You can use it for the either chemical web exploration technique, or you can take simple graphite sheet. You can exploit it by using the well-known scotch tape technique. You can do, or especially for your applications. So these are way, in fact, these are all large scale techniques. Again, I don't claim that graphene can be used for the our real battery. So still we need potential. So still people are using graphene as a coating, and we can compare with respect to what is the applicability of these materials for different type of carbon. Again, graphene can be used for different types in terms of the different type of, for example, water treatment. It's a different type of application. It's called composite, not alone composite application people are using. And sometimes people want to use some nitrites, carbides, and then so these are all the things you want to prepare. For example, ceramic composites for especially for future smart applications. I think we needed some composite material. Should be very hard. For that case, we can prepare by using this because this is a large scale applications. Not only for example building application, they want to be some materials. For example, in large scale, you can prepare by using this approach. So another one is sometimes you want to be battery material for a large scale. There's another way co-precipitation technique. And combustion, you want to heat it, decompose the material by using the simple the fuel and oxidizer we can using. There are all large scale preparation methods. And sometimes if you're a mechanical engineer, so you don't make it that, so you can mix the sample by using the ball milling approach in the sense that with the particle with a small ball to weight ratio, you can vary and we can get some nano sized material approach. So, and also sometimes these are the mechanical engineering work we've been collaborated. In fact, so that's why sometimes people want to see how the particle with the small fibers, how it looks like. Still, like I saw there in literature, people are studying with electrical engineer with a single, well, say nanowire with how the connectivity, and they're all basics. Again, single wire material, the connectivity is what they call strength. Those are the things also taken into consideration. Anyway, for the applications, we need a good mechanical strength are needed for your applications, etc. And we can do electrospinning and spraying and some hydrothermal and spray pyrolysis and some specific applications you need to coat the sample in a for example in a current collector, etc. So and also sometimes you can do the microwave, etc. So in fact, in summary, I think a lot of efforts have been made in literature, especially the smart material. I think the idea is that people want to look for the low cost and large scale. You can see there are a lot of literature. Since I don't have time to discuss, so in fact the Reddit belongs to our group, so we've been contributed. In fact, don't have much time to tell what is the real story about these materials. And sometimes we can climb some nano seems to better, and we check the impedance and some other type of materials have been looked into the literature, and also some of the main new materials have been contributed from our group. So I told you the nitrates, we tried to prepare thin films and bulk. I think they are promising. We demonstrate again the voltage is a little bit challenging, and sometimes these are the oxides. So I think these are the small contribution. We've been put some new materials we've been reported in the literature, and sometimes with respect to the positive, negative electrode, etc. So in conclusion, I think efforts have been made. So to prepare, for example, analyze or what are the storage materials, I think among all, only few materials are people are using for these materials for especially commercial electric vehicle and grid applications. So remember, the main issue is that, for example, that is the way, for example, now it is low cost, reduce the cost by 3 times is a major goal for our people, and safe and long life performing material is likely to come up. Especially the main issue is nowadays, I think sometimes there is a malfunctioning of the batteries or some problem with how to monitor the real health. I think we need a proper sensor. I think here the main role is that if any intelligent electrical or communication engineer, you can develop the sensors or some programming, we can do how to monitor the real health without doing any fantastic like expensive technique. I think you are able to do some what they call as some programming or something. You can tell us. I think that will be very useful. Again, at the end, so I can tell this is a research, it's not a one-person research. I think if you for any smart cities, there is a sensor, there is a batteries, and also there is a, for example, building. We need a civil engineers or like an architect, etc. And I think they're all the people who has to play an important role. So at the end, so I think we need a little bit education also. I think we have to see after doing all this one. So what my personal opinion is that as a young researcher, I think we have to see what they call it, we have to educate, especially any building or anything. I have to what they call as I think at the end what they call as after making a smart building any device, I think we have to take care of what they call service. All the responsibility belongs to like especially young people and all people who are responsible for any building or any smart city, especially for example solid waste management or throwing a dustbin in a proper way. So there are all things that made them to be a smart city. Again, thank you very much and really great, nice time to listen the talks, especially some of the interesting talks I learned yesterday. I think really challenging, and then I got some idea about like what physics I learned with the basic physics with previous talks. And thank you very much, sir. Okay, and then I think I'm already. I think I taken really 1 hour 21 minutes. I think I have another 9 minutes to take Q&A, and happy to answer if you have any question and answer. Okay, and then if you have any. Okay, since I don't have much time to discuss a real story here, I think we can go to YouTube. So many hydro technology, all this one is available. Or if you want to be large scale batteries are available in the net, I think that may not. Overall summary is that since as an academic researcher, I told about what are the possible techniques available for your research. And thank you very much, sir. Thank you. So 8 minutes I have. Thank you
Yes.
for Q&A.
Thank you. Thank you, Dr. Reddy, for
Thank you.
insightful delivery in this session, merging material science, ICT, and smart city, and giving multidimensional opportunity to all of us. Now, as far as queries concerned, few queries are I am seeing in the chat box of YouTube link. First one is there any alternative of lithium material for recycling purpose, for best recycling purpose?
Okay. So usually, alternative recycling is a different story. Lithium is the best one. Recycling, we can do either lithium by sodium. That is not a main issue. So I'm talking in terms of cost. Alternative to lithium is a sodium compound. That is the one. In terms of recycling, recycling is just like in metallurgy. The main issue with recycling presently we are facing is that for example, how much what they call as yield, because you know that you want to open the cell, all this one it comes, it depends on it. So since we go for hybrid vehicles or electrical grids, the amount of material is more, automatically yield will, so the yield will be higher, So as of now, presently, recycling technology that the people are facing what they call it, they're not in a profit one. That's why sometimes people are thinking about, for example, if you sell a battery, some of the cost will be included to the battery pack. Those are a lot of things are the government initiatives. Those are things is going on. Okay, since we have to protect the environment, so the way, so because we cannot get all the things, so that is a little bit problem, So that's why, for example, so the pollution. That's why people are thinking about no other option, So we have to
Okay. Another query is why XRF is not preferred for battery material analysis as compared to XRD?
Oh, it is very good question. Usually remember XRF is an X-ray fluorescence, okay, X-ray fluorescence. Remember that will give information about the elements, For example, so best way is that I'll tell you, suppose you see that, for example, uh, suppose, suppose in a food, there is we mix the things, we can see, visualize 1, 2, 3, for example, A, B, C. You can tell, oh, this food is there like that way. Real, if it is taste is not only, you can do the testing by using by test. Usually for material researchers, if the materials is pure or not, or in a proper phase, we can check by the X-ray only. Without X-ray, we cannot. All the XRF, it will tell the elements, For example, lithium is there, cobalt is there, oxygen. It will not tell what is this type of like hexagonal is there, cubic is there. So that is very important, For what they call as for battery material should be crystalline with a particular hexagonal phase. So this will form only at a particular temperature. So that's why X-ray is a fingerprint. In fact, I didn't, since I thought electrical engineer, it is, I used to put some few slides. Sorry for the, I think, okay, good. Okay. Sorry, I have, if you want, I can put some slides if I can tell. Usually the simple explanation is that X-ray is a technique to give the information about the diffraction based on the phases. That's all. Okay.
Okay.
XRF is the element sensitive to tell how much element is there. That's all. Okay. Based on XRF, we will not tell that really battery works. Mainly X-ray is a fingerprint. Okay.
Okay. Thank you. Thank you very much. With this, I must say final thanks to Dr. Reddy for accepting our invitation and for delivering an informative talk in this odd times as per your local Canadian time standard. It is, I think, too late in the evening right now there. Bye and have a nice evening there. Enjoy your dinner too. Bye, sir. See you on valedictory session too. Formally, I will send you the invitation for attending the valedictory session, just for sharing your views at that period of time. Please join the valedictory session, please.
Okay, thank you very much, and then good day, and then have a nice day. As Professor suggested, maybe don't miss the talks. I think that it will be good. That is my final suggestion. Okay, thank you
Yes.
very much, sir. Okay,
Okay, sir.
then I
Fine.
can. Okay, thank you
Please,
very much, sir.
please stop sharing the slides.
Yeah. That's why I can go out.
Yes, sir.
Okay, wait. Okay, so I.
A very good afternoon, good morning, and welcome back to second session. Here, I am delighted to have next invited speaker, Professor Sonali Chouhan from IIT Guwahati, India. Dr. Chouhan received her PhD degree from Indian Institute of Technology, Delhi, India in 2019. Since 2010, she has been with Indian Institute of Technology, Guwahati, where currently she is an associate professor in the Department of Electronics and Electrical Engineering. Her research interests are in the area of Internet of Things, wireless sensor networks, multi-axis edge computing, cognitive radio, embedded systems, green communication and networking, error control coding, energy optimization, and nature-inspired algorithms. Her research work has appeared in several international journals and conferences of international repute. Dr. Chouhan has worked in energy optimal IoT and wireless sensor network for more than 15 years. She is the author of multiple book chapters focusing on the energy efficiency of various communication techniques. He has been a project funded by leading industry partners like Intel India Private Limited and Nokia Research. With this, I welcome you, Dr. Chouhan, and invite you to start the session.
Thank you very much, Professor Taimur. I'm delighted to be here. I hope that I am audible properly.
Yes, ma'am. Yes, you are audible.
Okay.
Please share your presentation slides first, and then on bottom side, bottom right, one icon is there.
Yeah.
Present now.
So, is my screen visible?
Yes, ma'am. Yes, it is visible. Kindly go ahead.
Okay. Hello, everyone. Good morning. The talk today we are going to have is about multi-access edge computing and 5G for smart cities. So, as the theme of the FDP is related to smart cities, I thought that we can put very much things into context from the communication perspective. Not only communication, but some computation perspective also I'll bring into this talk. So this is what is today's agenda. We'll discuss what is 5G and their characteristic and challenges, and what are the enabling technologies available to make 5G more and more beneficial for us and making it more attractive. And then we'll focus on multi-access edge computing, what it is, what are the challenges, and we'll also talk about one of the major issues which we are going to face in new kind of applications, and finally I'll conclude. Okay. So in 5G, we all know that we are expecting very good data bandwidth, but at the same time, if we see the evolution which has happened from late 90s, 80s to till date, how things have added up. See, in first generation mobile communication from 1980 onwards, the focus was on voice calls only. Okay, and that prevailed up to nearly up to 2000. Later on, with um, 2.5G, which we used as GSM, some data communication with GPRS was enabled, but it was not very much. But comparatively, after 2000, your voice, in addition to that, web browsing has come into picture. So therefore, mobile broadband became one additional thing along with the voice communication. From 2010 onwards, when we have started talking about 4G and implementing it, we are focusing more on mobile video consumption and higher data speed. So not only we wanted to access the web, but we also wanted to share the videos and so on. And therefore, after 2010, it also included IoT, which could survive because we had good data speed available to us. And from this year, like we all know that 5G is very much a reality now. And from last 5-6 years, we were seeing that 2020 was the time to implement 5G in reality. So some big level uh, demonstrations were planned in 2020, particularly for 2020 Tokyo. It was planned in a very big manner, but unfortunately, because of this corona outbreak, all things have, I think, shifted, and therefore we do not know what is the status right now. We even do not know, although it has been said that in, I think, August 2021, the Olympics are going to be held if everything would become normalized by that time. Okay, so now the question is, beyond IoT, what is there? Okay, so that is what is, we have to look into 5G and its applications. So 5G is not only going to give us more data rate or bandwidth, but also this is going to give us some other dimension from the perspective of application. So we'll try to explore that what other type of applications we are talking about and which are possible here more frequently compared to which was not there in 4G communication. Okay, so what is the impact of 5G here? So it has given us many societal advancement. For example, we are talking about smart cities, and smart cities would require many smart technologies being implemented. For example, smart grid would be there, and this smart grid objectives are to not only bill or to manage the subscribers, but also to manage load, because from the back end perspective, if you see, you will find that many many grids are interconnected, and if their load has not been balanced out, then it becomes a very big problem and losses keeps on increasing. So from that perspective, smart grids are supposed to not only balance it on the fly, but also they are supposed to predict what is going to happen, and from learning from the experience, it can also predict that what is the best way or in what way it should be managed. So that is what is also being possible with the help of 5G. Then comes our IoT cloud, where multiple devices are connected and multiple users are utilizing these facilities, not only for communication as an individual, but also for many services which can utilize this. For example, for emergency situations, this can be a very good solution. For health professionals which are spread across the globe, they can also utilize this facility to provide some quality services at the remote places where physically it is very difficult to reach out by very high-end professionals because of some other limitations. Then comes the connections of the vehicles getting connected to each other, and traffic management in cities. So this will all, everything implemented here will lead to a smart city implementation. And in agriculture also, we can expect that like drones are there. So drones are not only being used for entertainment purposes. Like initially it was like it will simply hover around and take some videos or pictures, but for very serious uh, applications also now drones are being utilized. Okay. And finally, the medical services, as we talked about, individually what we can do, we can have multiple sensors, and those sensors can log the data in our day-to-day routine, and based on that some diagnostic or some inference can be made out. So normally what happens in some of the diseases, it is important that your regular data in which you are not very conscious or you are not monitoring only it for a very limited amount of time. If you are monitoring it for continuously for a longer amount of time, and that also without being conscious, because we all know when we become conscious, some of the vitals of our body will change automatically. So if we are not conscious about it, if we take it as a regular activity, and if by that time your monitoring is being done, that is more accurate data and will give us a better understanding. So this is also being possible with the help of 5G here. Another dimension in which it is impacting us is industrial transformation. In industries, robots can be deployed, and also not only they can be deployed, they can be controlled remotely. And in many machines, CNC kind of machines, you can very precisely control things. In industry, the automation may happen based on the output. If your output is increasing or decreasing, based on that, input can be calibrated. And your logistics, finally, the product when it is ready, that can also be monitored and also be logged in a better manner. That logistic management can also be done. And one very good application of this logistic management comes into picture. Earlier what used to happen, and right now also we are many a times observing what, that I have booked a parcel and that parcel is being tracked on the way, and what but when do we get the information? We get the information when it reaches to one hub. From there we see that okay, it has left hub number 1 and then it has gone to hub number 2 and so on. But in between those two hubs, what is happening still is not known to us. That is a black box. But comparatively, in some of the consignments, it is very important that you monitor what is happening in between. For example, in our coronavirus vaccines, we have learned that they require some specific temperature all the time. They cannot be kept on a very high temperature, and also some other precautions must be there. So when those will be moved from one place to another, it is important that continuously that would be monitored. Okay. So what can be done is continuously that can be monitored, and also that can be communicated. So as soon as if something is going to go wrong, not even when it has gone wrong, before it goes wrong, it can give you an alert, and accordingly some corrective action can be taken place. Then our agriculture, which is using many IoT applications, and also by using good bandwidth, or you can say multiple connections of multiple devices, can be utilized for monitoring soil conditions. It has how much moisture in it, what is the requirement of one place to another, because in a field all the time the requirements are not same. But so when we do it in conventional manner, we sometimes waste some of the precious resources. For example, we may do the watering, if uniformly try to do it, we may find that we have some place which is low-lying area, there water gathers. So if you have an idea where only you are supposed to give the water, accordingly that can be managed here. And then there are many unique experiences which are also being added. For example, virtual reality and augmented realities are two examples. In virtual reality, what happens that you are actually virtually sent to an environment which you are not in reality there. For example, you can be given a gadget which you can put on your in front of your eyes, camera fitted into a goggle kind of a thing. Okay, so there what you realize is as you move your head, one scene is being pictured to you. For example, the scene is of a seashore. So there what may happen is as you move your head from one direction to another, the scene also changes accordingly in a very fast manner. So see, you try to understand and try to appreciate that nobody knows that in which direction you are going to move your head and at what speed. So if you are moving it at a considerable faster or slower speed, accordingly it has to be adjusted, and it has to give you an experience that you are actually on that beach. Okay, there is a fine difference between augmented reality where the projections are being made virtually, of course, but this has to be augmented with your real-time environment. So that kind of experiences are really very unique and very interesting. For example, for virtual reality, what good applications could be you can think of. I can give you an example that on a historical site when you visit, if somebody is providing you the virtual reality experience, what can be done is there the scene on those places can be created and can be shown. So definitely it would help, and not only help but also increase the experience of the person visiting that historical site. So that can be a very interesting example which can be incorporated in real life. Similarly, there are multiple devices connected from multiple users at the same time. So that is also something which is happening very seamlessly nowadays. And 5G is going to enable it in a more concrete manner. So the more focus of 5G is on serving more number of people. And finally, the online teaching, online seminars, like we are also connected right now with online facility. So that way, that is also something which is going to be in an enhanced manner with the help of 5G. So what are the characteristics of 5G which are making it possible? One is that it is going to give me a very fast and high traffic data it is going to support. Okay. But at the same time, just now I elaborated some of the examples where 5G will be very beneficial or will be useful. You'll find that the computation is going to be complex and complex, because when you say that I am going to move my head in any of the 360 degrees, definitely accordingly the computation has to be done at that rate, and also experience should not be deteriorated. So from that perspective, you will find that it is going to create a very challenging environment. Not only experience is going to be good, but behind that experience, we have to encounter very complex computations. And definitely, as I said, that number of users are also going to be very much. Number will be growing very fast. Why number is growing? Because first of all, the spread is increasing, because everybody is finding that these facilities are very important. Sometimes this is like without this, the same life cannot be led. For example, in last 5-10 months, what we have seen is online education has become a mandatory thing. It is no more an optional thing. So the spread has been increasing, and not only spread is increasing, the number of devices with each users are also increasing. So like one person might be having 5 to 6 devices right now. he may not notice it. For example, he may have one or two mobile phones, he can have a smartwatch, he can also have some uh, shoe or footwear which incorporates some sensors. So that way you imagine that this is not a very big thing that one person is having 5 or 6 devices. And if you include the utilization in your home, which is going to increase day by day, number of users, or you can say number of devices, are going to grow exponentially. And one of the characteristics of 5G is that distances are going to be shorter. Why do I say that shorter distances? Because earlier days, what has happened that when we started with broadcasting of AM radio, then FM radio, it was limited to a city, but a big tower was installed and then whole city was covered. Later on, we moved on to satellite communication so that we can communicate from one continent to another very easily. Okay. But later on, as we try to move upward in our spectrum available, because in lower level, you saw that too much of crowding is there, and also it cannot travel too longer distances. But as we kept on moving upward in the uh, frequency spectrum, what has been observed that beyond a point, again, the smaller things, more obstacles are going to play a major role. Earlier, with our radio communication, the walls and bigger structures were not a very big problem. Even it could penetrate very big, thick walls, and you could receive the reception inside your home very well. But that is not happening with your mobile data. Even that is not going in very high frequency range. Same is with your satellite communication. You have to install one antenna outside your home to receive the signal. And similarly, what is happening that in 5G also we are thinking of utilizing higher frequencies. And as you go on doing so, better that you have shorter distances and line of sight. So from that perspective, 5G is going to incorporate short distance communication. Of course, we can use relays, we can very fast move data from one place to another, and that is how we can achieve a larger coverage area. But from point to point, this is going to give you a constraint on the distances it is going to cover. Definitely, if such things we are expecting, associated challenges we cannot ignore. So what are the challenges? The power consumption should be low, because mostly devices are becoming now battery operated, and also they are being closely used by the human beings. So you cannot tolerate a higher power consumption, because that is going to generate heat and you cannot tolerate it beyond a limit. Plus, with higher computation complexities, you require better and higher processing capabilities. Of course, reliability is another dimension which requires a very good attention. And to survive longer, for the batteries, it is required that you manage your load in a manner that they do not die down very fast. Because it is very inconvenient that you keep, even though you have rechargeable batteries, very inconvenient to recharge them very often. And many applications also require that the latency is very small. So we are talking here in terms of millisecond latency. So these are the challenges which we have to overcome for implementing 5G for the applications we are looking forward to. So with various objectives, various technologies have come in which have made that okay. There are promises that this can be tackled using this technology or other technologies in the similar domain. For example, we have throughput enhancement as the objective. If I want to increase the throughput, so you can utilize waves for the higher bandwidth. Advanced carrier aggregation techniques can be used to increase the throughput. Cognitive radios are there which will enhance the throughput overall by allowing non-licensed user to use the licensed spectrum. and also massive MIMO or 3D beamforming. Uh, uh, so number of antennas, larger set of antennas are also going to help us in achieving the same. Another dimension of doing so is different types of modulation and codings will have to be implemented with available computational resources. Higher order modulations and advanced channel codings are becoming more and more default things. Plus, different advanced multiple access techniques have come in, like non-orthogonal multiple access is there, or your filter bank multi-carrier technique is there, or FTN, which is faster than Nyquist signaling is there. So these are all some non-conventional approaches. Why these are non-conventional? I'll just explain in a while. And then advanced interference management techniques, for example, successive interference cancellation or transmitter receiver cooperation or network coding, all those can also help us in increasing the throughput. But if I change my objective from increased throughput to flexible topology, because in some applications it might be important that I cannot work with a fixed topology. So can I have something more flexible so that scalability can be very well addressed here? So your advanced relay techniques or wireless backhaul, or you can say that cell-free networks are going to cater to this objective. Then another objective could be low cost and low power, because that is also is one of the important factors. If I have to implement 1,000 devices to make something happen, definitely I am very much concerned about the cost and also the power consumption, because it has two impacts. One is the utility and second is the life of battery. So for that also some techniques are there which can be utilized. For example, device to device communication is there. You can integrate transmitter receiver with the wireless LAN or wireless PAN areas. Okay. So overall, what is happening? This is a paradigm shift. In what manner? See, initially we started by talking about massive MIMO or MIMO. So there things were based on orthogonal signals transmission. Okay, but now we are moving towards non-orthogonal. For example, in case of non-orthogonal multiple access, as the name itself is suggesting, do not use orthogonal pilot signals or orthogonal signals for communicating data. So definitely we have all learned that if two signals are not orthogonal, some residual would be there. So because of that, some challenges are there, but we thought, okay, we will try to mitigate it in another manner. But advantage of doing NOMA is you can incorporate more number of users, because you have limitations on number of orthogonal signals generated and processed. You can generate theoretically infinite number of orthogonal signals, but at the same time, the processing for those infinite or very big number of orthogonal signals will pose another type of challenges. Similarly, we said that, okay, we want to go with Nyquist signaling, but faster than Nyquist is saying that, no, we don't want to follow it. We are in fact using it in a manner that it increases the inter-symbol interference. Earlier we were against it, but now we are deliberately increasing it. And therefore, earlier the technique, either it was orthogonal or in MIMO, or giving the data rate such that it doesn't include any ISI. We were in the regime of no interference to now we are introducing interference deliberately. And in case of NOMA, it is, if you have worked with it or if you have a very preliminary idea, you will find that superposition coding is being used, where multiple users are sending the signal in a superposition manner. So that has been clubbed together because they are sharing the pilot signal, okay, carrier signal. So therefore, it is going to introduce user interface. We are doing it on a deliberate manner. Similarly, FTN is also going to improve the inter-symbol interference. Otherwise, in any communication regular text, you'll find that we want to avoid ISI. But what we are doing here is we are introducing ISI on the pretext that, okay, whatever user interference or ISI we are going to introduce, we know how to tackle it, and we will try to remove it so that we can gain advantage in another dimension. Another paradigm shift is happening from centralized structure to decentralized or distributed structure. Earlier, we talked about cellular structures. It was having one base station and it was centralized. Now we are going towards cell-free MIMO, that is decentralized. Similarly, multi-access edge computing is also another example of distribution. Earlier, we had cloud computing, in which in the center of your cell, you can say one cloud server is there, which is placed very remotely from you in some situations. But we said that, okay, that is going to create problem. We'll talk about what problem it is going to create just in a while. So the option proposed was you use edge computing. So you put many number of servers, but distributed in the cell, so that on the edge also some server is available to you nearby. So that is how we are shifting from conventionally what we have been practicing till now to something non-conventional here. So that way it is very challenging as well as very interesting. Thinking out of the box actually is becoming a reality here with 5G coming into picture. And we are having very much expectations from the system. We expect that applications should perform very well. They should perform in a very small time, so latency should be very less. Also, we require more throughput, plus it can compute a good amount of data. Like when we go from HD to VHD or even Ultra HD kind of resolution, definitely lots of computation is involved in processing it and giving it to you in front of you. So all these things are expected, and we are working so that it becomes more and more a normal thing, not an exceptional thing. So what is the solution for these expectations? See, we were thinking about that application can perform better, it can give us better throughput, latency should be low, and more computational load can come. So my mobile device, whatever I do, will be always face that it has a very limited resources. Therefore, can we share our load with the central server? That is what the solution initially thought about. Okay, so therefore the cloud computing came into picture. But over the time, what has been observed, that if you imagine that there is a circular cell and cloud server has been kept at the center of the cell, and if you yourself is near the periphery of this circle, okay, so how much time it is going to take to communicate your data to the cloud? It will take more time. Similarly, the cloud accessing time is more for the edge users. Okay. Not only that, there is one cloud and multiple users are there. So definitely, if load on the cloud will increase, the latency automatically will increase, because you will be in the queue and simultaneously serving so many users will be a problem for one server. And over the time, people have realized that maintaining such a server is really a very expensive job, because you have to provide a very big data center for it, and you have to give it a continuous power supply. Not only that, you have to keep the backup so that if something goes wrong with the hardware, you do not lose the data. So that way some redundancy has to be maintained, and maintaining the cost of maintaining such cloud servers is very, very high. So what is the solution? Solution is you go with edge computing. So edge computing suggests that you place the servers close to the users. Okay. So when you place the servers close to the user, it means we are suggesting that you now shift from one centralized server to multiple edge servers. Definitely, this is saying that, okay, I can work, because the same amount of load it has to tackle all together. What can be done is every server in the edge computing can be a little bit less demanding, or a little bit less storage capacity wise as compared to one cloud, because you have multiple now edge. So altogether they can compensate for the capacity cloud was allowing me to have. At the same time, the advantage is, as it has been placed very close to me, I can access it with the same latency as any other user is doing, because he also has one or more edge servers around him. So you can have one edge server, or you can have more than one edge server. So there are multiple problems here which people are solving. That how this scenario is going to help us. Definitely, this is a promising solution and really an interesting one. Okay. So the multi-access edge computing came from this logic of putting an edge server closer to the user, and it is also known as referred to as mobile edge computing. So initially it was referred to as mobile edge computing. Later on, the more formal definition has come in, which has not only included mobile devices but other devices as well, and now it has been referred to as multi-access edge computing. And it allows mobile devices to share their loads of computation, as well as it can be used for storage of data. Why these two things are different? See, I have 15 files with me on my mobile. So what I can do, instead of keeping it in the hardware of my mobile here locally, I can upload it to any edge server, as I was earlier doing with my cloud server. Okay, so that I can access it anywhere, anytime. Not only that, now we can think, as this is coming closer to me and it has much more capability than my mobile device has, I can think of sharing some load of my computation also to the server. So therefore, we can think of this as an energy efficient alternative to the cloud computing. That is what is something very interesting about this edge computing, multi-access edge computing. Okay. So again, from where we get the motivation? We get the motivation that my mobile device has very limited storage. Okay. It also has limited computational resources. So one may argue that no, my mobiles are becoming more and more capable enough. Earlier days, you had simple processors. Then we started having dual core processors on mobile. Now quad core processors are also old thing. Octa core processors are very normal thing, and that's also not very expensive. I agree with you. But you think from the perspective of the demands as well. Earlier, you wanted just to browse the internet and wanted to access your emails. Okay, fine. Later on, when the processing capability increased, you also then started playing some games which were local to your device. So you used to download an app where you can individually play a game. So it required some graphics in it, some moving around here and there. So it needed more processing definitely as compared to surfing the web. Fine. Later on, we said, no, no, I'm not happy playing alone. I want to play with my friends. So therefore, we came with applications which are actually network playing ground. So now everybody is sitting at different geographical locations, and then they are one. So imagine that now you have to map in to map the resources only based on your requirements or your moves. But relative to this, now with multiplayer, there are 10 players means 10 minds. So the degree of freedom is increasing enormously. So that computational resource, which is growing, of course, but still my demands are also increasing vis-a-vis the computational resource enhancement. So therefore, like always lagging behind. So same is happening. The batteries were not as can't imagine a 5,000 milliampere hour battery 3 years thing nowadays. But at the same time, we are for a singular web service loading lots of data. Earlier, concept which was called ADSL. So that was like asynchronous DSL technology. So what people did at that time, that they have observed that you most of the time download data and used to upload data. That was very the web. What happens? You download more data and you upload less amount of data. What is your uploading data in conventional manner? Only you are writing an email, so that is an upload, so other direction. But you are reading through some news portals, you are visiting some websites, you are visiting your employer's website, and then so that way our upload data was less and download data was more. So from that perspective in ADSL, what was done that, okay, they kept upload bandwidth less and download bandwidth larger. But relative to that, now you imagine what is happening today. Today, your upload has also increased a lot. On WhatsApp, we are sharing messages. We started doing that with GIF or other animations. Later on, multiple video messages started being shared. So I have, if I am uploading or I am sharing, the other person is downloading. So the ratio is now becoming more, we can say that the contribution of upload is also increasing as compared to download. So from that perspective, you see that our resources demanded for the applications are like enormous. So you want more and more resources. Your octa-core processor is also at one point of time not enough to process your requirements. Okay, so as we have made growth in all the directions, but still my requirements are growing simultaneously, and always my requirements are more than what is available with me. So that is why it is very relevant that we find out some other ways. Can we take help of some big brother like edge computing server? Okay, and therefore in any scenario you will see, you will find that, okay, always I have a shortage of computational resources, always I have a shortage of battery. And what is the solution here? So what we say is, okay, we can the mobile devices can use multi-access computing servers, edge computing servers, to store the data and also to offload its computation. What is the idea? Idea is, if you can promise me a faster delivery, I'll give you the job, you complete that job and give it to back me. One may argue that how is it going to save resources? Okay, so it is going to save resources in the manner that my edge computing server is not equivalent to my device. It is much more powerful. It can do the same computation faster. Therefore, it will be doing it in a smaller amount of time compared to me. And but we all know that this is not going to be free. So some way we have to incorporate what are the costs involved here. Okay, but as a solution, we can think of that whenever I'll have requirement of more than what I can do on my mobile device, I'll let it out to the server and I'll utilize it. Okay, fine. So we stick to this idea in case of multi-access edge computing. Okay. So how it extends the cloud, this picture will elaborate it in a more concrete manner. So you see there is a cloud here, which is central to the, which is in the central area of my server. So you can say that this is the core of the network. Still, we are not talking about removing cloud. Okay, for some purposes, cloud may be good. Then there is a fog computing in between. We haven't talked about fog computing. I'll let you know what is fog here. And finally, this is the edge. So on the edge, we have some servers which are distributed. And this fog's job is, you can think about this as in between cloud and edge server. But major job of the fog is to offload some of the data from the edge server towards the cloud. See, for longer duration storages, for offline storage transfer, the cloud servers can be utilized by the edge servers, because from my perspective, I have given it to edge server and then I can be free. but edge server is not as big as one single cloud server. So therefore, what can be done is, over the time when user is not involved, the edge servers can transfer the data to the cloud. And normally in that transfer, in between these two layers, we can imagine that fog servers or fog computing would come into picture. Okay, fine. So this says that mobile edge computing is going to extend the cloud to where people and objects are connected. So it's like bringing it to your doorstep. So this is like bringing the computation to your doorstep. And what advantages we are going to have? Certainly, better user experience is one of the things. And if I can ensure some good amount of network-based service innovations, will good amount of services here, some service innovations will take place, and innovative services towards subscribers, enterprises, and different verticals also are going to be available to us. So that is what we are envisioning with the multi-access edge computing. It is quite an interesting technology, and it has lots of promises. So therefore, we will find that not only the multi-access edge computing is going to be a part of 5G, but also this is going to be a part of 6G. So this is not going to get stopped only by 5G, but in the next generation of 6th generation communication, this is going to become one of the very basic and very important enabling technologies. Okay, so what are the advantages here? This is getting closer to the people, and this is connecting objects. So when we say it is coming closer to the people, you should not forget that we are in the era of Internet of Things. And therefore, when we say people and things are very much interchanged now. When I say that I am connected to network, I mean to say all my devices are connected to the network, and therefore many devices can connect to, and so therefore the connected object is becoming a reality with it. And we can expect that network edge environment will provide us with ultra low latency. Also, it will give us advantage of the proximity with the server, and definitely higher bandwidth is one of the advantages here. And it will also have real-time insight into the network and context information. That is what is important. Plus, it can have some location awareness. How it may be helpful, you see that if things are connected well, and you are at a location where some of the things are different than another location. So if location awareness is there, accordingly better decisions can be taken. If you are in a location where 3 or 4 servers are there, you can utilize those 4 servers in a different manner. How? Either you can choose one which is very close to you. How closeness works for me? Because more close you are to a resource, you will require less amount of, you can say that attenuation of your signal will be lesser. Okay, so therefore you can say that your quality of signal is going to be better. Okay, another way I can do is, I'm not very much concerned about it, or I can say that all the servers are more or less similarly placed from the distance perspective. I can say that no, I have so much of data. Can these servers collaboratively do the work? Why should I rely only on one server? So it is like, instead of choosing one single best server, I would like to choose more number of servers together. So there we can think of utilizing more number of servers available to me in a collaborative manner. So that way we can think of going towards the network coding in a more realistic manner, and they can do part of the jobs, different parts of the job, and then that can be stitched together again on the mobile device. Okay, so that is how the mobile edge computing is going to allow us to think of many new scenarios which were not possible with cloud computing because of its different structure. Okay. So what are the applications we can think of mobile edge computing? See, one is connected cars. Various cars are there, so they can be connected to one of the servers placed nearby, and they can transmit the information to nearby cars wherever things are not visible. For example, in this left panel of the picture, you see that a two-wheeler is going on, and there is a big truck going on the right of this two-wheeler. So he has no idea if there is a junction, somebody is coming from that side or not. So that may be sometimes dangerous because you have no idea what is happening. So you can see that on the left panel we have shown a top view here. So what is happening that along the side of this truck there is a junction coming up and some movement of the cars is happening, which you have no idea locally. But if you have some connection here from one application, car or one vehicle to another, you can easily let the other know that there is a danger ahead, so you be careful about it. Okay. Then another one is edge video orchestration. For example, you have been watching a football match or a cricket match in a stadium. So normally what happens, we also get the live telecast of the match at our home through the channels. Okay, fine, that is okay. But at the same time, what may happen is with everyone having one device with him, mobile itself, you can record the videos. You can also, instead of recording, I want to stream it. So instead of, like, what happens when it is streamed to everybody, that has not been customized. Comparatively, if I am actually watching this match on the stadium, what I can do is I want to show to my relatives, my close near ones, some interesting part of it, which I find interesting, and I know that they will also find interesting, which is not possible with any local channel distribution because they are not customizing it. They are in fact generalizing it and they are giving it for everybody's requirement. And imagine if this is a last over of the cricket match or some very end of the football match where penalty kick is been given. So what happens is that at that time multiple users would like to stream that particular moment to the server. So at that time the mobile edge computing can be very helpful, and their multiple streamings can be supported without having a problem. Imagine this in a stadium. In a stadium, many users are likely to stream a very turning point of the match. And if you think of using the cloud service for that, I don't think that is going to support. But comparatively, if we have many edge computing servers available here, that can very well support this kind of a streaming. So that can also be an application. Another one is video analytics. So what may happen is that you have a camera. You are actually trying to monitor some area. Okay. And let us say that example we take here to reduce the or to notify the intrusion detection. So normally what may happen, very first thought is, okay, I keep on streaming it to your home. But see, I can't keep on watching it indefinitely, right? Because intrusion will happen only once in a while. But other times things are all well and good. So what can be done is the edge host can in fact do some processing here. So every time the live feed is given by the camera to the edge node, but it will process, it will see that whenever there is a problem, okay, then only this is going to tell me that some problem has occurred. So whenever it will see that some intruder has come in, it will notify it only at that particular point. So whenever there is no event from that edge host, no streaming will be done. So therefore, you don't get to deal with unnecessary data. But whenever the event would be detected, it is going to notify you and also going to give you the live feed So that way it can be managed in much more efficient manner. Okay. And as we have talked about AR and VR, so as I said that VR means totally it is a virtual reality. So it's virtual as well as it is becoming a reality. And similarly in augmented reality, you can see on the right panel that one girl is doing some experimentation where she actually doesn't have this flask available physically, but she can imagine that she has a flask. So that is what is the augmentation in the real world. So real world doesn't have it, but some of the part of it has been augmented by the virtual things, and that is how you can imagine, and not only imagine, you can do so many things together over there. So these are very, very interesting applications. So what applications will find it very much useful? One is those who have huge processing in it, those who have lots of data to tackle, and those who have some real-time processing to be done. Okay, so like your AR VR requires real-time processing, what you are doing here should reflect in the processing. Similarly, your high quality video streaming will be dealing with big data. Lots of data would be generated, and real-time gaming will be also coming in the two parts. One is huge processing plus real-time processing. So various applications will be more or less requiring that I can process a lot, I can process a lots of data, and I can process a lots of data in very small amount of time. So this is what is we are expecting here, and we are trying to make it possible. Okay. So the challenges here is that I cannot process a lot with limited battery. So I have to save energy of my battery. So I would like to offload it to the server. Okay. But what happens when I do the offloading to the server? See, as I said, there is a saying NFL, no free lunch. I don't get anything for free. I have to pay a cost. Only thing is I can evaluate that how much am I gaining and how much am I paying the cost. Is this making the deal win-win? Am I gaining more than what cost am I paying? Then I'll say that, okay, I can still bear a cost. Okay. So one very first cost which you can imagine is I'm transmitting the data to the server, and in return I am receiving the data back to my device which has been processed. So let us keep our system very simple. Imagine there is a mobile device. Imagine there is a single server. Okay. So when I think that my mobile device will not be sufficiently able to handle the data, what I'll do, I'll offload it to the server and tell that what job has to be done. There can be various types of jobs. Okay. So based on that type of job, your return amount of data will also be depending on it. We'll discuss about it just in a while. But while I'm giving it, see, I have to wirelessly transmit. So wireless transmission is not free. It will also require some energy, because when I'm transmitting data through Bluetooth or Wi-Fi, you imagine that my battery is getting drained. So similarly here also for data transmission, I have to spend some energy. Okay. Second is I have to receive the results back to my mobile device. So that also is going to consume energy. So I cannot forget it. Okay. So now with that perspective, the question arises, how much data should I offload? You can imagine if I offload too lesser data, then my overheads are lesser, but at the same time gains are also lesser. But if I keep on transmitting too much of a data, my overhead of transmission and reception will overcome the advantages of reduced computation load on my device. So the major question here which we are going to tackle is how much data we should offload. Okay. So there are two ways of doing it. One is binary data offloading, second is partial data offloading. What is the binary data offloading scheme? Binary data offloading scheme says, okay, you either you just evaluate whether downloading the full data is good or not. If you find that, okay, overall with everything together, the cost borne by me is lesser than the advantages it is going to give me, I will be fully transmitting the whole job to the server. And if it is not so, then I'll be keeping that job with me and I'll process it on my mobile device. Okay, fine. So that's why we call it binary. So decision is in 0 and 1. If beneficial, offload everything. If not beneficial, keep it with you and do nothing. Comparatively, there can be another approach that, okay, I do not do the full offloading or zero offloading. I can also do, of course, in addition to 0 and 1, something in between. What is something in between? 10%, 20%, 30%. Why to offload full data? If I can still have an advantage with 50% of data offloading, I can do 50% there and 50% will be kept on my mobile and I'll process it on my mobile itself. So interestingly, that raises another question, how much? See, in binary, it was only two things, one decision, 0 or 1. But now I have increased the levels. So at what level it will be more beneficial? So that part we have to think about. While doing this, it is important that my data or my application should be such that which can partition the data in more organized manner, so that some percentage can be taken off the mobile and some can be kept here itself, and later on that can be merged together. Okay. So when we go with binary data offloading, it is like you have to take a very small decision. You do the computational cost analysis based on the whole data available to you. And what is the analysis here? See, you add the cost of transmission, you add the cost of reception, okay? And based on it, you also take into account that what you're going to save. So what am I going to save? I'll try to estimate that how much energy am I going to invest if I process this data, full data on my device, okay? So this technique is useful when I cannot divide my jobs into subparts. Unless and until I can do that, I can think of the other technique, which is partial offloading. Okay, so if your application says that I cannot divide the data into parts, you have to then think of only one logic, either fully offload or you do not offload it. So what is the disadvantage of this approach? The disadvantage is that you cannot utilize the parallel computation facility available to you. What parallel computation facility you have? See, I have given a scenario of very simple one user, like one mobile device and one edge device. So therefore, still I can use my mobile. See, instead of giving a job to somebody and then sitting idle is not a parallelization. Instead of that, if I can do at least, let us say 10% of the job, while the server is doing 90% of the job, definitely I'll be saving the 10% which was supposed to be done on the server, and also saving on the transmitting and reception of that 10% again. So that way, I cannot utilize that advantage at the in case of binary data offloading. Contrary to that, if we go with partial data offloading, so we require that my application can divide my data and utilize it later on into subparts. So what are the examples of such applications? One is video streamings, your images. So you can actually divide your whole video stream into number of frames, and you can process some number of frames here and other part of the number of frames at some other place. So that can be very well managed, and finally that can be again stitched together. Okay. And now this considers how much data to be offloaded. So now my question is not related to only 0 and 1 single threshold, but it also asks for me that if I consider other amount of data offloading, then which one is the best here? Okay. And it will be having the advantage of utilizing the parallel computation facility of the mobile device as well as the edge server. Okay. So what is the cost of offload? One is see, in any cost analysis, I have to see what is the saving and what is the expenditure. Simple. So what is the energy saving here? As computation is performed by the computationally powerful server, and also I can assume that my server is not too much of having energy constraint. It can be plugged in the power from the main supply, and it is not working on any battery like my mobile device is doing. So I can think of that, okay, its cost is not as stringent from the energy perspective of the computation as mine. Another thing is, it is definitely much more stronger as compared to my mobile device, and therefore I can save on the computational part. So imagine if I am offloading on to the server, I'm not doing anything. If I'm doing full offloading, means I'm not doing any processing on my mobile device. I'm simply waiting for it to be received. Another energy expenditure is I have to transmit and I have to receive the data. One may say that how much it is going to cost me, and will it be comparable? So for that, we have to see that what is the proportion of my computational energy consumption and how much is the proportion of my data transmission expenditure. Because these two come from very different domain. One comes from the RF energy being transmitted, so that is a part of communication, and another the computational resources that comes from the computational part of my resource. Okay. So another thought here is that, okay, if my cost of transmission or reception is becoming more and more, I can do one thing. I can compress the data. So if I do the compression of the data, what additional step would be required here? I have to compress and decompress as well. So that is one more computational cost I am thinking that we can involve. But at the same time, I am reducing my expenditure, energy expenditure, just now we have talked about, which was the due to transmission and reception. So if I reduce the amount of data by compression, I will save again on it. But again, NFL, no free lunch. I have to pay a cost. Okay. So question was here, can we compress the data and transmit or not? Okay. So definitely without adding the additional cost of it, the question cannot be answered. Okay. So what we observed that for short distance communications, where the distances are not very large, not large means in few meters when we are talking, and as I said that with 5G and 6G, the newer generation, the communication distances are going to be smaller and smaller. At that time, your computational costs and radio cost, the communication, the RF part cost becomes very much comparable. So this is one of this particular pie chart is showing three parts in it. One is computation energy consumption ratio, radio communication energy consumption ratio, and the base energy. What is base energy? See, while I'm not doing any job, still my circuitry has to be up. So to keep everything ready to be in a position to transmit or receive, or ready to be in a position to compute, I need to keep on constantly spend some energy, and this is the base energy. So this result we obtained by measuring the energy consumption for a small sensor node, so that we can know that what is the ratio here. Because why is it important? See, this is very important before we proceed. Why? Because if you change the ratio here, forget about the base, simply the radio and computation part. If I make this computation part, let us say very, very thin slice, okay? So will it make any sense for me to consider the computational cost? No, because whatever I do, even if I reduce 100% of computation cost, I'm gaining only a part of the whole picture. But comparatively, when these two are very much comparable, I have a plenty of room in both the scenarios, so I can do some jugglery here, so that I can either increase computation and reduce radio more, or vice versa. So this we know, this we have. Think about this is how we have to think about here. Okay. Okay, fine. So what we are proposing here is that we will have an application, and of course, in which network scenario you are deploying, that is also is a very important thing here. So that is going to determine together as what is your data size, because from application your data size is going to get decided. Your network deployment is going to tell me that what are the distances for communication. Another thing from the application would come in as how much bit error rate you can tolerate. So normally what happens if your applications are changing from one to another, you will notice that your requirement for losses which you can tolerate is also different. Very simple example is reading a text versus reading a medical transcript of someone. So in a text, even if one word is missing, it doesn't make a difference, much of a difference. I can try to guess also what was written over there, but in medical transcript that may make a hell lot of a difference. So therefore, based on applications, my requirement on the error rate I can tolerate will also be determined. Okay, and definitely based on my network deployment, what is the bandwidth being used, what is the carrier frequency, and all those things will be determined. And based on all this, we can have some energy model, which will model the one part that is radio energy. Second is it can also take into account the computation energy into account. And third is your codec energy. Codec energy is coming here because of the compression we are introducing. Okay. Finally, based on it, we select one particular configuration. Here, configuration means 10% of the offloading we have done, 20, 30, and so on. And finally, we find out that what is the energy consumption, and out of this, we can simply find out which is the best one. Okay. As the problem has been simplified, we can try to imagine it in a much better manner. Okay. So, how do we make an energy model? Energy model here will be of two types. One is for having the energy model of radio, we have lots of theory behind, and therefore we have many models available to us. And but at the same time, for computational one, no theoretical models will work well, because every time computation technology is changing very fast, and we don't have those models available as well. So we rely on the simulation models for the computation facilities, which are of course available to us. Okay, and definitely the accuracy of this model is going to determine the accuracy of our result. At the same time, we want that this should work faster so that I can take better decisions in small amount of time. So I should not, so always there is a trade-off, but here two requirements we are going to fulfill. One is it is faster so that my abstraction level is higher. And second, this is going to give me a better decision, more accurate decision, closer to the accurate one, so that my decisions are not wrong. Okay. So by keeping these two things in mind, this is what is we have the this is what energy model we have proposed, where we are dividing the edge server energy and mobile device energy separately. Out of that, only mobile device energy is energy constrained, so we'll focus here. And from the device architecture perspective, you see I have a local computation here. Okay. Then we have a codec part which will do compression for the before the transmitting data, and also after receiving the data from the server, we'll do the decompression. Okay. Then comes the radio part which will transmit and receive. So how we have done it? See, here we have taken a total data as D. Out of that, we thought, okay, lambda is the data proportion to be offloaded. So 1 minus lambda of D will be locally computed. Lambda will be compressed and transmitted. Okay. But after compression, this is no more a lambda D data. This has become based on my compression ratio of gamma. Your total transmission will be gamma times of lambda D to mobile edge servers. Okay. But when it has been processed on the edge server, what comes back may not be the same data. Imagine the application where I have only to process the video to find out whether the event has occurred or not. So what will be the response? Yes or no. Okay. So that way my return data is very less. Another example could be I am processing the video for the game purpose. So the amount may be the same as I transmitted. So therefore, we also have introduced one variable here, mu, which is the ratio of output to input data at edge server. Okay, so therefore this mu could be 1, this mu could be very close to 0, or mu could be larger than 1 as well. So based on that, we can think that, okay, this is the amount I transmitted and this is what I am going to get back. Finally, it goes to the receiver, then decompressor, and after the decompressor, the gamma part is removed, and finally I get the mu times of lambda d data. Okay, fine. So this is how we can imagine that this is the scenario, and based on it, we can process the data. So radio part has circuit part and RF energy into transmit and receive part. So we have utilized our energy model from the analytical models available, which says that based on my bitter rate requirement here, PE is the determining thing. Based on it, I can determine that how much transmit power I have. So in other words, for a given transmit power, I can compute that how is the SNR going to be received. And finally, for that SNR, how much energy am I consuming? Okay. And another is based on how much is amount of data. Because if amount of data will increase, the time my transmitter will be on will be larger. Okay. And one more factor here is of power amplifier efficiency. So based on the efficiency of my power amplifier, which is used in practical purposes, this can be calibrated. And last part here is about circuit, which is going to contribute to the base energy. Okay. Then comes your compressor and decompressor codec energy. Okay. For that, we have used we have taken the example of high quality videos, and therefore we considered the latest thing, which is HEVC compression. And we have used Kawasar encoder for implementing it. This is implemented in C, and therefore we can think of having this encoder as a function of X and Y. Okay, where what is X? X is transmitted data, and Y is the received data. So amount of data will increase or decrease based on this encoding or decoding part will also change. And finally, we are considering for local computation. So we are considering the generic energy model here. And here also we have considered different local computation models, C1 and C2. So which says that what is the order of computation is being done, whether it is less or whether it is more. So we have introduced K here, which will take care of this particular phenomena. Okay. So these are various parameters here, which we can say that we have taken the video quality from WVGA to HD, FHD, WQHD, and even Ultra HD. So this is 8K video, which is the latest one available. So what are the results? So quickly I can summarize that if on the x-axis I have fraction of the offloaded data, y-axis I have the mobile device energy consumption. So with various values of K, so depending on how much is the cost of computation on my device, we see that different answers I'm getting. So definitely this says that depending on what is your cost on the mobile device, how much proportion you can offload, the answer is going to be different, but our framework can be used to determine what is the best offloading percentage. Okay, like here it is 50%, then it becomes 70%, and then it becomes 80%. Okay. Another one is whether compression is viable or not, whether it is totally not viable because you have too much of load of compression and decompression. But what has been observed here is, you see that the solid 1, 2, here this is without compression, the circles, and solids squares are with compression. So anywhere the circles are without compression and squares are with compression. So relatively we have 3 different scenarios we have taken. And we have taken Ultra HD data as also, and for WVGA data also we have done it for various values of K. So what we have seen in different scenarios, we found that partial offloading is still beneficial, and also we can use compression here to overall save the energy. Then data size, see different streams will have VGA to UHD. Different data sizes will be created for the same set of video. So therefore, as the data size is going to change, my answers are also going to change, but that can be figured out with everything taken into account. Okay. And finally, the what is the impact of location of the edge server? So if you are going to change the location from 250 meter to 1 kilometer, you see that your answers are again changing. But our framework can take that into account very easily and can give you an answer that what is the percentage of data you should offload if your server and device distance is X, Y, or Z. So in conclusion, the 5G networks are going to pose new challenges and therefore we require some new solutions. And of course, without reliable data transmission, nothing makes sense. And therefore, we also have to, for the sake of feasibility, my battery consumption is going to be a very major concern here, primary objective. So looking at it, one of the solutions we have discussed here in today's talk. Okay. So thank you very much for your time. And I also take the opportunity to thank the organizers for giving us a very good opportunity to connect. So now we can take some questions if you have any.
Thank you. Thank you, Professor Sonali, for your nice talk delivery. I was searching any relevant query in the chat box of YouTube channel, but the participants have written the appreciation for your talk, not any query. That is a good thing that everything was clear to the participants. With this one, I must say final thanks to Professor Sonali Chouhan for
Yeah, thank you very much, and I really thank everyone, the participants who have listened to it and also appreciated it. Thank you very much,
thank you
everyone.
and see you on the valedictory session scheduled on 15th Jan at 3:30 p.m. Please join valedictory session too, if possible, ma'am.
Sure, I'll try my best to be there.
Okay, ma'am.
Yeah.
Bye. See you.
Uh,
Now,
thank you very much.
now, before proceeding with the third session, we will take lunch break till 1:30. Then after that, at 1:30 p.m., next session will start.